Hello. Hi. We're gonna start in about 5 minutes. Hopefully the connection is gonna be all right. It was really unfortunate Tuesday because the internet sucked, but hopefully, well, it all works out today. Hi everyone. Welcome to the stream. Hmm. Okay, so it seems like the sound is okay. All right. How is everyone doing? So once again, I'm planning to stream for about 4 hours, perhaps five. We'll see. And today, hopefully, we're gonna finish the first section of chapter 2, outer measures. Hi, Ryan. Thank you very much for joining the stream. So, even though this is only the first section, it already contains several non-trivial results. So today we're going to cover two important results at least. That's the plan. The first one being the outer measure of the closed interval. So we wanted closed and bounded interval. So we wish to show that the outer measure of the closed interval a to b, where, here, I mean, we can assume that a and b are both finite. If, let's say, if a is minus infinity and b is positive infinity, then there's nothing to be proved. Okay, so here we're assuming that a and b are both finite. That's the first result we wish to show. It looks completely trivial, right? So the length of a to b closed interval. Actually, sorry, the length of the open interval a to b is defined as b minus a, but wish to show that the outer measure of the closed interval is b to a. And it turns out that it's not an easy result. So that's the first thing we wish to show today. And the second result we wish to show is the non-additivity of outer measures. So far we've been dealing with only the good properties of outer measures, but here in a bit, okay, perhaps in the second half of the stream, or perhaps even sooner, we will see that outer measures are not additive. Okay, if you have two disjoint sets, the union of their union will have an outer measure that is not always equal to the sum of the outer measures. This is highly non-intuitive. And one of the reasons that measure theory is very difficult is because um, the constructions tends to be very unnatural if you've never seen it before. Okay, so that's uh, that's the plan. Okay, so hopefully we will finish both today, both major results today. And always, as always, questions are welcome because, as I mentioned repeatedly, this is not a lecture series, but rather I would like to consider this as a seminar. So I would like to encourage as many questions as possible. There's no such things as stupid questions in the stream because, um, you know, and measure theory, as I mentioned, is very difficult even for someone that is who's well prepared in elementary analysis. So we wish to achieve an understanding we would like to achieve an understanding that is totally internalized. So the end game is be able to construct the theory from scratch. So the end game is to be able to construct the theory in your head. That's what we're going about, instead of treating this as a bunch of information to be absorbed. Okay, if we treat this simply as information to be absorbed, you will not have a very solid foundation. You can pass the exam, perhaps, but that's not where we're going about here. All right, so just to briefly remind ourselves, what's the progress here? So we wish to show that the outer measure of the closed interval a to b is b minus a. Okay, and just to briefly remind ourselves what the definition of outer measure is. So going back a few pages, here we have the definition of outer measure. So it's defined as follows: for any set A, that is a subset of reals, what we're doing is we wish to consider a sequence of open intervals whose union contains A. So this is called a cover of A. And so a cover is a collection of sets that contains whose union contains the set A. And we're only using open intervals to cover A. And then once that cover of open intervals of A is selected, we can take their total length, that's the sum of the lengths of ik, and we're just going to pick the infimum, or the greatest lower bound, for all such infinite series, and the result is called the outer measure. So the idea is really intuitive. So by the way, it's called an outer measure because we are using intervals to contain A. So this is A. You're going to use a bunch of intervals whose union contains A. So the whole union is, you can think of it as the outer is out of A. Right. So there, it's not in this book, but there is something called inner measure. Okay, there is something called inner measure. So you can imagine what would be an inner measure. What would be inner measure? So inner measure is the opposite. You can once again select a bunch of open intervals, but instead of covering A, they are covered by A. They're covered by A, and then you're just going to take the supremum. And then you're just going to take the supremum. Actually, that would not make sense. You would insist these intervals are covered by A are disjoint. Okay, so that's the inner measure, but that's not what we're dealing with here. We're dealing with outer measure. So in outer measure, we want a sequence of open intervals whose union contains A, and then we just take the infimum of their total lengths and call that the outer measure. Okay, outer measure has some nice properties. For example, a finite set had outer measure of 0, countable set had outer measure of 0. Okay, and it preserves order, aka monotonicity, and it is invariant under translation. So these are all properties we've seen and proved. Here, countable subadditivity is also a nice property. Countable subadditivity, but here we wish to show the outer measure of a closed interval a to b is b minus a. Okay, so how do we go about doing that? Well, we can first pick a sequence that looks like this: a minus epsilon and b plus epsilon. So graphically, this is what's the sequence looks like. So that's the closed and bounded interval, and you have a minus epsilon, b plus epsilon, and a whole bunch of empty sets. So the only non-empty set is the first one. Okay, and of course the outer measure of the first open interval is b minus a plus 2 epsilon. Right? And the outer measure, being the infimum of the infinite series, has to be less than or equal to b minus a plus 2 epsilon. And because epsilon is arbitrary, is positive and arbitrary, so the outer measure is less than or equal to b minus a. So that's one direction of the equation taken care of. But now we need to prove the other direction, which turned out to be much more difficult. Okay? The other direction, of course, being the outer measure of a to b is greater or equal to b minus a. Right, so we wish to show that. In here, let's just remind ourselves why this is not trivial. Because the completeness of R has to be used in some form, as said by Axler. Indeed, if R is a countable set, by the way, R being uncountable is a consequence of the completeness. Remember, we talked about this in our first stream. Right? R is defined as the set of real numbers in elementary analysis, and that's the first lesson in elementary analysis, is defined as the complete ordered field. It's complete ordered field, so the completeness is what sets R apart from Q, right, from the rationals. And we know that rationals are countable. Right? So if R does not, if you don't use completeness, right, then R is indistinguishable from Q, and Q is countable. So if Q is countable, then the outer measure would be 0. Right, so we just said that the outer... Man, my provider sucks. I don't understand, so this is highly unusual. This whole week has been like this. Yeah. Sorry guys. When was I cut off? When was I cut off? So I was talking about the non-triviality of the other direction, which was a review of the last stream, but I don't know if I was cut off. That really sucked. Yeah, I know. Sorry, Caliburg. This is really annoying. You know what? I'm not sure if you guys know, but people in Canada pay for some of the most expensive internet in the world, but also at the same time some of the worst internet in the world. This is just incredible. Well, what can I say? It's just I mean, I hope, like, perhaps the internet in the US, the provider in the US does a better job, but in Canada it's just like this. Like I'm using quote unquote the best network in the country, and it's just incredible. And still as jerky as this one. Okay, but anyway, hang on. Let me just continue. So here, we're going to use something called the Heine-Borel theorem, which is on the next page. But for that, we need a few definitions. Okay, so we need something called essentially compactness. Okay, essentially compactness in terms of open cover. Okay, this is something that is quite difficult by elementary analysis standard. Arguably the hardest definition and notion to wrap your head around in elementary analysis. So don't be frustrated if you've never seen this and feel this is difficult. It's supposed to be, okay? It's supposed to be, and don't worry, we will get through that. So basically, we're going to define the compact set, basically, even though it's not mentioned as such in the text, but basically we're going to define a compact set. So what is a compact set? Compact set is a generalization of a finite set. Okay, so compact sets in general aren't finite in terms of cardinality. but it enjoys properties of finite sets, okay, or at least analogs of finite sets. And one of them is called data compression principle. I mean, this is my own language. So basically, I made a compactness video a few months back. You can search it on the channel. It's quite long. It's purely on the definition of compactness because I think it really worth taking that amount of time. So compactness essentially is a sort of finitude for infinite sets. Okay, so one of the ideas was what I call data compression principle. So what does that mean? So if we take a finite set and cover that with a family of sets, okay, remember a family of sets that covers the finite set just means the union of that finite set. Hi George Payne. So the union of that family contains the finite set. And it doesn't matter how big that family is, you can always extract finitely many elements in that family, in the original family, such that their union still contains the finite set. You can always do that for a finite set. Right? This is what I call data compression principle. So essentially, the definition of compactness is is the data compression principle. And so this is how we define compactness. So here we have a subset A, which is the subset of reals. A collection C of open sets of R is called an open cover. So an open cover is a collection of open sets of A if A is contained in the union of all the sets in C. So in topology, you write something like this: the union of the scripted C contains A. Okay, so here's a diagram for that. There's the Venn diagram. This is your set A. I'm not drawing this on a real line because the notion of compactness really extends into a topological space that you don't need a real line to discuss compactness. So basically, you have a set A, and all these circles together, they form an open cover. So in an open cover, the elements are these sets. All right, and each of them is an open set. So, and an open cover is said to have a finite subcover if A is contained in the union of some finite list of sets in C. So the finite subcover is a subset of scripted C. So it's a finite subset of scripted C. Remember, as I said, scripted C is a collection of open sets. The idea is you can extract a finite subset of scripted C so that these finite sets still covers A. So that's the idea of a finite subcover. Okay. If we continue this definition, we can add an extra bullet point and say A is compact. So that's literally the definition of compactness. A is compact. Okay, let me just stop using cursive. Okay, A is compact if every open cover of A has a finite subcover. Every. So that's the definition of compactness. In general, it is much easier to show a set is not compact than showing a set is compact. Because if you follow the definition, to show a set is not compact, you just need to give an example of an open cover that doesn't have a finite subcover. Right. So let's see some examples of these two notions, an open cover and subcover. So here we have, let's draw a picture here following the examples in Axler's text. Okay, so here let's consider the set, the closed interval 2 to 5. Example. Hi Wendell, I still have to watch your videos on compactness. It has all definitions, exactly. Well, I didn't talk about quasi-compactness. Okay, I just talk about compactness. So in my video on compactness, I was just, I motivated it, okay, by calling it an extension of finitude, a finite set. So compactness seems to be a natural next step for, and a natural generalization for finite set. Okay, so that's how we go about proving it. So anyway, and notions such as compactness and paracompactness are sort of a relaxation of compactness. But compactness is essentially what drives much of the elementary analysis. Okay, I once posted a quiz in my community tab that asked for the following. So, which of the following major theorems in elementary analysis has nothing to do with compactness? It does not rely on compactness. 1. Intermediate value theorem. 2nd, extreme value theorem. 3rd, mean value theorem. And 4th, continuous functions on a closed and bounded interval is Riemann integrable. So those are the 4 results. And only one does not rely on compactness. And the answer is intermediate value theorem. Intermediate value theorem only requires connectedness. Okay, and everything else has to do with compactness. So, so this is quite substantial because extreme value theorem and mean value theorem are both highly important results, as well as a fundamental theorem of calculus. A fundamental theorem of calculus, FTC, relies on the mean value theorem. So as you can see, this is how compactness pretty much underpins the foundations of calculus. But anyway, compactness is in general very a profound property in topology as a whole, but we're not going to be get into there. Okay, so here let's just take a look at a few simple examples. So here you have the set A, which is the closed interval 2 to 5. And then we also have the collection. Okay, so what's the collection? So the collection, let's call it scripted C, is indexed by K, and which consists of open intervals K to K plus 2. And K is positive integers, so K is 1, 2, 3, and so on. Of course, this is an infinite collection, a countable infinite collection, in fact. So let's draw the set C, okay, not the collection C, scripted C. The first one is 1 is 3. The second being 2 to 4. The third being 3 to 5. And the fourth being 4 to 6. The fifth being 5 to 7. And so on. Okay, so to cover 2 to 5, you just need how many? Well, just need 1 to 3. You need that. Why can't you just pick 2 to 4? Well, 2 to 4 is an open interval, so you need something that covers the endpoint too, so 1 to 3 is mandatory. And 3 to 5, of course, and 4 to 6. You need 4 to 6 because you need to cover the endpoint 5. And everything else after is redundant. So scripted C has a finite subcover. And let's write that down. The finite subcover is 1 to 3, 2 to 4, 3 to 5, and 4 to 6. All right? That's the finite subcover. So we can say the open cover scripted C has a finite subcover. However, we cannot, based on this example, and declare A is compact. Why not? Because in the definition it says every open cover of A has a finite subcover. High rough. So every compactness is every open cover has a finite subcover. This is only one. Scripted C is only one open cover. Right? So as you can see, why showing a set is compact in general is difficult, because you need to show any arbitrary open cover has a finite subcover. Here we just have one example. That's not enough. But let's continue. Right? So let's continue. So this is example 1. Example 2. Let's continue reading. The collection, you see this is the same collection, k to k plus 2. K is a positive integer. Is an open cover of the closed interval 2 to infinity. So let's draw that. In fact, we can just borrow the same picture pretty much and change the right endpoint. Right? So here, in our new diagram, the right endpoint is infinity. Okay. Okay, so that's the new set. And here, A is 2 to infinity. Scripted C is still the same set, same collection. It does not have a finite subcover. Scripted C is obviously a cover of A, but it has no finite subcover. Why? Because if it is a finite subcover, if it has a finite subcover, then there's an open interval whose corresponding k is a maximum. Then the union of the finite collection would have bounded length. Which is impossible, because the length of 2 to infinity is infinite. It has no finite subcover. So this should be obvious. So this has no, scripted is a cover of A, is an open cover of A, but it has no finite subcover. Of A. Okay. Once again, very simple example, but in the language of compactness, we can immediately say, well, the interval 2 to infinity is not compact. It's not compact because we found an open cover of A that has no finite subcover. The definition of compactness says every open cover must have a finite subcover. Here we have a open cover that has no finite subcover. Therefore, it is not compact. So as you can see, showing a set is not compact is in general much easier than showing a set is compact. Let's continue. So now we have an interesting scenario. We're looking for an open cover of the interval 1 to 2, an open interval 1 to 2, example 3. So let's draw this a bit more carefully. 1 to 2. This way. So A is the open interval 1 to 2. Okay, and we emphasize that we don't include the endpoints here. This turns out to be super important. Okay, and 1 and 2 are does not include any of these endpoints. Okay, the collection scripted C is now what? The collection scripted C is the collection of open intervals 0 to 2 minus half k. Sorry, 2 minus 1 over k, where k is 1, 2, 3, and so on. So let's draw that and see if that's an open cover. Of course, these are open set. Is that a cover for A? Let's find out. Okay, so I'm just going to ignore the scale here and declare this is 0. Okay, it does not really matter. So the first, when k equals 1, obviously it's just 0 to 1, so that's the first interval. So that's the first open set in the collection, 0 to 1. The second would be 0 to 2 minus 1 half. 2 minus 1 half is 1.5. Okay, so that's k equals 2. Okay, so this is k equals 1, this is k equals 2. When k equals 3, you get 0 to 2 minus 1/3. The 2 minus 1/3, 1/3 is 0.333 and so on. So that's 0.167. Okay, so basically that's what k equals 3 looks like. So as you can see, as k increases, the right endpoint of these open intervals is moving towards the right. Right? And when k is very large, say k is 1000, then the right endpoint will be extremely close to 2, but it's still not quite 2. Still strictly less than 2, but it's very, very close. So the picture would look like this. So for very large k, the right endpoint would approach 2. Okay. Large k. And it keeps on going. Okay. The union of scripted C is 1 to 2. And in fact, this deserves its proof. This deserves its proof. So let's write that down. So let's claim that the union of scripted C contains A. Obviously, it does not equal A because you got this part 0, 1 that's wasted. Okay. Okay. The union of scripted C. In fact, we can write it as 0 to 2, and we'll prove it. Okay. So let's prove it. The union of scripted C is 0 to 2. And obviously, this claim would imply the union of scripted C is a cover of A because 0 to 2 contains A, 1 to 2. Okay, so let's prove that claim, shall we? So to prove this part, okay, just to prove proof of star, you would need a double containment argument. So let's start from one direction. So let X be in the union of scripted C. Let X be in the union of scripted C, and which means this is the union over K from 1 to infinity, 0 to 2 minus 1 over K. Okay, and what we need to show is we need to show X is in 0 to 2. And here we go. So by assumption, by our assumption, namely X is in a union, X belongs to one of such open intervals, 0 to 2 minus 1 over K for some K. For some K equals 1, 2, and so on. This is by our assumption. And as a result, X is less than 2 minus 1 over K and greater than 0. And that's exactly what we needed, because we need to show x is greater than 0 and less than 2, right? We already have that. It's greater than 0 and less than 2 minus 1 over k, which is less than 2, as needed. So this is very simple. Wendelin says union of a finite subcollection would be yes, yes. So game over for compactness. Exactly. So this is an example that is not compact. Okay, A is not compact. That's the upshot here. So here we have what we're going towards is that here descriptive C is a open cover of A that has no finite subcover. Exactly. So Wendelin is saying this is why 1 to 2 open interval is not compact. So once again, the thesis is showing something is not compact is much easier than showing something is compact. Okay, so here we have two concrete examples that aren't compact: 2 to infinity and 1 to 2 open interval. Okay, so but that's what we're getting to. But here let's just finish the claim. So this claim shows descriptive C is an open cover. Right? Just to make sure there's no funny business going on at the endpoint 2. Okay. So even though the elements in descriptive C are all a little bit to the left of 2, the whole union still contains A. So let's just verify that and make sure there's no funny business going on at x equals 2. Right. Yes, we found one open cover that has no finite subcover. Exactly, Rolf. Right. Descriptive C is that open cover of A that has no finite subcover. Ergo, A is not compact. Right. So, guys, let me just get some water here. I'm getting thirsty. All right, I'm back. Okay, so to prove the opposite inclusion, Wendelin says sequential compactness feels more natural to me than subcover open set. I'm not sure which one is. I feel like they're equally hard for beginners. Sequential compactness, Baldon and Weierstrass and Heine Barrel, they feel equally difficult for beginners, in my opinion. It really is a matter of which one you're exposed to first. Okay, the one you're exposed to first is likely to be quote unquote easier for you. But I don't think there's something intrinsically harder, harder with, say, open cover than the sequential compactness. Of course, Wendelin is totally correct that the two notions, sequential compactness and compactness, are equivalent in real, in fact, in metric spaces in general. So sequential compactness defines compactness using sequences. Here we're using open cover, and that's what we're going to stick with. So it appears to me, okay, that in measure theory, probability, as well as topology, the open cover version is used more often. The open cover version of compactness is used more often, whereas in functional analysis, the sequential version is used more common. In their most general setup, okay, in topological spaces, sequential compactness and compactness are different notions. Okay, they aren't sufficient or necessary for each other. But here we're just sticking to the open cover version because you see, we're still in the subject of outer measure, right? In the definition of outer measure, you're trying to cover things. You cover things using open intervals, so that's what we're trying to do here. Okay. Anyway, so here let's just finish this proof real quick. Okay. The opposite direction requires the Archimedean principle, I believe. The opposite direction. So now the opposite direction of star. Let x to be in 0 to 2. And you need to show x belongs to the union of scripted C, i.e. x belongs to one of the open intervals, at least one. Right? X belongs to one of the open intervals 0 to 2 minus 1 over k for some k. And so on. Okay, so how do we do that? Well, by assumption, x is less than 2, obviously. X is less than 2, and therefore 2 minus x is positive. 2 minus x is positive. So I'm going to use a property called the Archimedean property. I believe it's in Axler's supplement, but I'm not going to go over that because I can just state the result real quick. It's quite straightforward. So by the Archimedean property, is that how you spell Archimede? By the Archimedean property of R, there exists k in 1, 2, 3, and so on, such that 1 over k is less than 2 minus x. Okay, so the idea is for any positive real, okay, you can always find a reciprocal of a natural number so that the real number is bigger than the reciprocal. You can always do that. You can always find such k. So as a result, for this k, let's call this k star. Okay, for this k star, we have x is less than 2 minus 1 over k star. And since x is positive, so x is in 0 to 2 minus 1 over k star as needed. So this proves the opposite direction. So indeed, the union of scripted C is the open interval 0 to 2, even though all the intervals in scripted C has its right endpoint strictly less than 2. If I recall correctly, in the field, Archimedean and the limit of 1 over n are equivalent. Yes. Yes. All right. So that's the claim. So this proves the claim. This proves star. Okay. So the idea is scripted this set A. Hang on. The scripted A is sorry, not scripted A, but A 1 to 2 open interval is not compact. You have a closed, you have an open interval that has you have an open cover scripted C that has no finite subcover. Now, Archimedean, there are always larger integers, or 1 over n can be arbitrarily small. Exactly. You are completely right, Rolf. There are two versions of equivalent. There are two equivalent versions of the Archimedean property for real. So one, you can state state that the set of natural numbers is not bounded. The set of natural numbers is not bounded in R. And second, 1 over n can be made arbitrarily small, exactly. So Archimedean property the second version of the 1 over n can be made arbitrarily small can be equivalently stated as there is no such thing as an infinitesimal in real. Yeah, there's no such thing as an infinitesimal in real. So if you want to really talk about the infinitesimal rigorously, you would need a non-standard analysis, a hyperreal, okay, which I'm not terribly familiar with. Okay, so I'm very much educated in the old school analysis. Okay, non-standard analysis is now mainstream, but still somewhat less known. Okay, not the majority of the mathematical community heard of them, but isn't well versed in it. Okay, anyway, so that's the third example. So basically, I think through these examples, it is we can grasp the idea of open cover, finite subcover, as well as compactness pretty solidly. Okay, maybe not compactness because we haven't seen an example of a compact set yet. Okay, so which brings us to the next result, okay, which is extremely important, Heine-Borel theorem. But first, let's finish up this block of comment by Axler. The next result will be our major tool in the proof that the outer measure of a to b is greater or equal to b minus a. Although we only need the result as stated, be sure to see exercise 4 in this section. Okay, we'll check that out for sure, which when combined with the next result gives a characterization of the closed and bounded subsets of R. It gives a characterization, namely sufficient necessary condition of the closed and bounded subsets of R. Okay. Note that the following proof uses the completeness property of the real numbers by asserting that the supremum of certain non-empty bounded sets exists. Okay, so the next result is called the Heine-Borel theorem. The Heine-Borel theorem says every open cover of a closed bounded subset of R has a finite subcover. Okay, so here it says closed bounded subset. It doesn't say closed bounded interval. It's called closed bounded subset. So for that, we need to review two notions. I think we only need the Heine-Borel theorem for the closed bounded interval, but let's just briefly review what a closed and bounded subset is. Okay, so a set, let's call it F, which is a subset of real, is closed if the simplest way to define that is by saying F complement Fc is open. That's one way to define it. In fact, that's how topology, how closeness is defined in topology. There are many different ways many different equivalent ways to define closed sets, but here you can just say Fc is open. That's the quickest way to define closed sets if you know what an open set is. Okay, and bounded set, let's say a set B is bounded. Well, we've seen bounded set before in the first stream. Is bounded if it is bounded above and bounded below. Both bounded above and below. Namely, B has an upper bound and B has a lower bound. So that's it, okay? So it doesn't have to be a closed bounded interval. Although closed and bounded interval is a special case of closed and bounded subset, of course. Okay, so Heine-Borel theorem says if a set F, if a subset of R, okay, is closed and bounded, you verify these two assumptions, 1 and 2, then immediately you can say every open cover of it has a finite subcover. Okay, so let's not look at the proof of this theorem. Okay, so let's just briefly, let's skip the proof for HB theorem for now and see why this is useful. Okay, why this is useful. So Heine-Borel theorem in itself, the proof makes use of the completeness axiom, as we shall see. But the major goal here, let's not lose track of the main goal, is to show that the outer measure of the closed interval a to b is greater or equal to b minus a. So what we want is this. Okay, HB is only a mean to an end here. So let's see how that is applied. Okay, I think we understand the statement of HB. Okay, even though we haven't looked at the proof yet, right? We understand the statement of HB, but we just want to see how it is applied in showing the result that we wanted. Okay, so let's go. We're going to skip the proof for now. We'll come back to that later, but let's see how this is done. 2.14. Outer measure of a closed interval. Suppose A and B are real. So by the way, here A and B are real in the sense that they aren't infinite. Okay, we're not talking about extended reals here. With A less than B. Then the outer measure of A to B, closed interval, is B minus A. Okay, nice. See the first paragraph of the subsection for the proof that the outer measure is less than or equal to B minus A. Okay, we've already seen that. What we want is the opposite direction. To prove the inequality in the other direction, what do? Well, let's suppose I1, I2, and so on is a sequence of open intervals such that it covers the closed interval a to b. Okay? Then, by the Heine-Borel theorem, Heine-Borel theorem says what? The Heine-Borel theorem says every open cover of a closed bounded subset of real has a finite subcover. Well, the closed interval a to b is closed and bounded. And here we have an open cover of it, I2 all the way, I1, I2 all the way, right? So this every set in the sequence is an open interval, therefore is an open set. And their union contains the closed interval a to b, therefore it is an open cover. Apply HB, we know there is a finite subcover. We know there's a finite subcover. And because there is a finite subcover, in that finite subcover, the index for I has a maximum. The index, right? So because you extract it, suppose we know the existence of a finite subcover, that means we can extract a finite sequence. A finite, a finite collection among I1, I2, and so on. And you just pick the largest index and call that n. Okay? And you pick the largest index and call that n. A to b is obviously contained in the union of I1 all the way to In. So this is the usage of HB theorem. Okay? We now prove by induction. We now prove by induction on n that the inclusion above implies that that the inclusion above implies that the sum of Lik, k ranges from 1 to n. Basically, that's the total length of the subintervals. Sorry, that's the total length of the intervals in the finite subcover. The left-hand side is the total length of the intervals in the finite subcover. That's greater or equal to b minus a. Okay, and once we have that, the original sequence, I1 and 2, the infinite sequence, must have a total length that is greater or equal to b minus a. And because the original sequence, I1, I2 is arbitrary, I1, I2, and so on is arbitrary, right? So this inequality holds for arbitrary sequence I1, I2 that covers a to b. And therefore, by taking the infimum on the left-hand side, we have the outer measure of a to b is greater or equal to b minus a. Okay, so the key now hinges on 2.12. So 2.16. Question, do we not get that inequality for free from the finite subcover? Yeah, you do get that for free from the finite. Sorry, you get this for free. You mean you get this for free? It should be quite obvious, right? It should be quite obvious, but let's just see why. Wendell, you see, yeah, you mean 2.16, you mean this should be obvious? Because I1 all the way to IN, well, I mean, we want to, the thing is you have to suspend your intuition, right? We have to, whatever we do, we have to quote a definition or a result we have earlier. That's the thing. So because of this containment relation, can we, so yeah, how do you get 2.16? Why is that obvious then? Is it because you want to say something along the way that the outer measure of a to b, is less than or equal to the outer measure of I1 union all the way to IN? Is that where you come from? Because 2.15 will give you that. This is true because of monotonicity. Remember, we have that here. If you have A is a subset of B, then the outer measure of A is less than or equal to the outer measure of B. Right, so 2.15 will give you this. 2.15 will give you this. Right, and let's look at the right-hand side. The right-hand side obviously is less than or equal to the sum of the lengths of Lik. And that's by the definition of outer measure. That's by the definition of outer measure. Because I1 all the way to IN and empty set is a sequence that covers the set I1 union all the way to IN. But the problem is, as you can see, this is circular. So we wanted to show the outer measure of A to B is greater or equal to B minus A. You see the circularity here? So you see, by claiming the inequality is free, you're saying what you're trying to prove is obvious. So it's not obvious. Right. So that's the thing. So whatever we claim, it has to come from a definition of a previously proved result. By monotonicity, we have this. By the definition of outer measure, we have this. But somehow you need to connect the outer measure of A to B with B minus A. All right. So let's. Does that answer your question, Wendell? Okay. So let's take a look at the induction argument. Are you talking about subtitle in Spanish? I don't know. Okay, right now I can't, but perhaps for recording I can put a auto-generated Spanish subtitle. So to get started with our induction, note that 2.15 2.15 clearly implies 2.16 if n equals 1. Hang on. I think our goal is to prove 2.15 to 2.16. Right? That's the idea. So why don't we just call that a lemma? Huh? Why don't we just call that a lemma? 2.15 implies 2.16. Let's call that a lemma. Let's formulate that in our notes. Lemma. For any n equals 1, 2, and so on, I'll answer your question a bit. So for 1, 2, n equals 1, 2, and so on, if a to b is contained in I1 union all the way to In, then the outer measure, oh sorry, it's not the outer measure, then b minus a is less than or equal to the sum of Lik, k from 1 to n. Let's just add the extra specification that I1 all the way to In are open intervals. These are open intervals. So then you have this inequality. So that's our lemma here. Okay, so we wish to prove this, and this is a statement about the integers, the natural numbers, so we can prove it using induction. I mean, we'll see. But okay, question by ILO. So using the definition of coverage and then the HB theorem and then the definition of measure theory, so does the first inequality follow? You mean the first inequality in the sense of 2.16? Yes. If that's what you're talking about, then yes. Because if you have 2.16, then b minus a is less than or equal to the infinite sum of Lik. And this inequality, okay, the part I'm highlighting here, now works for every sequence of open intervals that covers a to b. And then taking infimum on both sides, you get what you want. So now it's just a matter of proving 2.16 from 2.15, which I call the lemma. Okay, let's see how that's done. To get started with our induction, right, so you have a base case. Right, base case, so that's obvious. So if you just have I1, on the right-hand side in 2.15, then by monotonicity, no, not by monotonicity. If you just have a to b being a subset of I1, I'll answer the question by Rolf a little bit in a minute. Okay, so if you just have n equals 1, that means, well, you can write I1, call it as a prime b prime, say I1 is A prime B prime open interval, then A prime is less than A, which is less than B, which is less than B prime, and you would have B minus A less than B prime minus A prime, which is exactly the length of I1. Okay, so that's proven. Okay, so we'll write that down in our notes. This is too messy. Hi Vernon. Rolf asked for L of A union B. Yeah, L of A union B. Can we assume subadditivity of length? Can we assume subadditivity of length? Good question. What do we have here? Right? Everybody has access to Axler, right? Can we something we cannot assume or something we can assume is strictly follows strictly from the order of exposition. Do we have that result here? Do we have the length of the union is less than or equal to the sum of you're talking about, Rolf, you're talking about the length of A union B. So first of all, by writing little l, remember little l only applies for open intervals. Okay, I'll answer here. It seems like a lot of confusion going on, so I'll address these questions one by one. So Rolf, when you write L of A union B, you're assuming that A union B is an open interval. So little l applies to open intervals only. And if that's the case, I think you can prove the subadditivity. So what you're saying is, if A union B is an open interval, then okay, A, B themselves are open intervals, first of all. And the union is an open interval as well. Then you should have the length of A union B less than or equal to the length of A plus the length of the interval, the length of the interval B. I think this can be proven. Proof is the exercise, but it's not relevant to what we're trying to do here. Or at least it's not directly applicable because we don't know if this is we don't know if this is an interval. It should be. I think it should be. I think because I think this should be an interval, I1 all the way to IN. This should be an open interval, but you have to do extra work to justify that. Okay, let's just follow the proof here. So ILO asks, why does it use induction after the first inequality has been proven? Well, here you see, this is a lemma which we aim to prove by induction. The lemma says for any n equals 1, 2, and so on, if the interval a to b is contained in I1 all the way to IN union, where I1 all the way to IN are open intervals, then we have b minus a less than the sum k from 1 to n, the length of ik. So what we're trying to prove is 2.15 implies 2.16. So that's why we use induction, because this is a statement with the statement that works for all n, right? So it's the statement that works for all natural numbers, and for such statements we can often explore the argument of induction. Right, so and as all induction arguments, you start from the base case n equals 1. Okay, so now let's go to the induction case. Okay, so as I was saying, our goal is to show that 2.15 implies 2.16. You see, we will now prove by induction that the inclusion above implies 2.16. So we're trying to prove 2.15 implies 2.16. Okay, and this is something important. So, okay, we're not just proving 2.16 in general. Okay, we're assuming 2.15 and prove 2.16. And for that, we're going to assume suppose n greater than 1 is fixed. Okay, suppose for some fixed n greater than 1, we have this property. We have 2.15 implies 2.16. So what does that mean? It means for some fixed n, suppose for some fixed n, okay, this is not an arbitrary n anymore. Suppose for some fixed n, I say that once again, suppose that for some fixed n, if you have n open subintervals, if you have n open intervals, I1 all the way to In, that covers the closed interval a to b, then the total length of those open intervals must be at least b minus a. So that's what we assume. That's the induction hypothesis. Okay, suppose n greater than 1 and 2.15 implies 2.16 for all choices of a and b in real with a less than b. What we wanted to show is 2.15 implies 2.16 works for m plus 1 also. Works for m plus 1 also. So ILO saying, let's see if I understand correctly. We need to prove the inequality of the sum. Yeah, we want to prove 2.16, and we'll use induction on n with respect to the sum. Yes, I mean, essentially, I think your idea is correct. So what we're trying to prove is an implication. Okay, that's the lemma. That's a lemma. That's an implication. If you have this containment, then you have the inequality. Okay, so the whole statement, if then, that's a full proposition. So that's a full statement, and that proposition depends on n. Depend on n, and we claim this is true for all n, and that's why we're using induction argument. Okay, so here we have stated the induction hypothesis. Okay, and what would be the goal here? What would be the goal here? So the goal is to show 2.15 implies 2.16 works for m plus 1 also. So you're going to assume 2.15, but in this case you have n plus 1 instead of n. So that's why we're doing. That's why we're writing the next sentence. Suppose I1 all the way to In plus 1 are open intervals such that the closed interval a to b is contained in the union of I1 all the way to In plus 1. Okay, so what does that mean? What does that mean? Well, here we have a little diagram here. Okay, it says B is in at least one of the intervals I1 all the way to In plus 1, exactly. Right, because B is a point in the set on the left. B is a point in the set on the left, and it belongs to. It must belong to the set on the right, the union. Therefore, B must be in at least one of the intervals. Okay? By relabeling, we can assume B is in n plus 1. Okay? So relabeling does not hurt. Right? That's totally fine. We can assume that B is in In plus 1. Perhaps for ease of writing. Now you can always or perhaps for ease of writing you can always do so. Okay. All right. So let's write In plus 1 to be C to D. Once again, remember this is an open interval, so we can assume In plus 1 has the form C to D. Okay. There's one trivial case. If C is less than A, Right? If C is all the way here, okay, if C is all the way here, all the way left of A, then what? Then the length of IM plus 1 is already greater, right? Is already greater than B minus A. So there's nothing further to be proved, right? Because if one of the lengths in the sum is greater than B minus A already, then the whole sum must be greater or equal to B minus A. So that's a trivial case. So now let's assume that C is greater than A. Okay. So you can assume that C is greater than A, and because B is assumed to be in IM plus 1, and IM plus 1 takes the form C to D, B is strictly less than D, and B is strictly greater than C. So that's the scenario we're interested in. Okay, so that's the scenario we're interested in. Okay, and what else here? What can we go from here? Well, hence we have A to C. The closed interval A to C is contained in I1 all the way to IN. Why is that? Why is that? Let's be very careful here. We have A to B. We have A to B is contained in I1 union all the way to IN plus 1. And IN plus 1 is C to D. IN plus 1 is C to D. So let's consider let X to be in A to C. Let X to be in A to C. Can we show that X is in one of I1 to IN? Can we do that? Well, X is in A to C. First of all, X is in A to B. Right? X is in A to B. And therefore, X is in I1 all the way to I1 union all the way to IN plus 1 because of this. Let's suppose for a contradiction that X is not in this one. Let's suppose for a contradiction that suppose X is not in I1 all the way, I1 union all the way to IN. Suppose X is not there. Then what happened? Well, X is in A to B. Hang on, I'm still struggling to see why AC is contained in I1 all the way to IN. IN1 union all the way to IN. So why is that? Why is that, huh? A to B is covered by the union of n plus 1s. So X belongs to the complement then. So X, Wendelin says, X is not in IM plus 1, so must be in one of the previous intervals, as X is in A to B. Hang on a second. So X is in A to C. This means X is not in IM plus 1. You're right. This is really simple. So, yeah. So because X is in A to C, that means you don't need this. That means X is not in IM plus 1. But because x is in A to B, right? Because let x is in A to C, therefore x must be in A to B. X is not in IM plus 1, it must be in the first n subintervals. Yeah, you're correct. Yeah, when that's an excellent argument. Okay, so we have this, and now we can use induction hypothesis, and that's pretty much done. Right? The sum of Lik, k from 1 to n is greater or equal to c minus a. And then you just add one more, and c cancels out. So this completes the proof. So the lemma is proved. Yes. So yeah, I'm just going to restate the part where I got stuck and helped out by Wendelin. Thank you very much. So y is A to C must be contained in I1 all the way to In. So let's start from an arbitrary element x in the left-hand side, A to C. Since x is in A to C, x is not in In plus 1. But because x is in A to C, x is in A to B. Therefore, x must be in I1 union all the way to In plus 1. And we just say x is, and we just find out that x is not in In plus 1. So therefore, x must be in the union of the first n subintervals. So starting from an arbitrary element x in the left, we proved it is also an element in the union of n subintervals. So therefore, this containment argument holds. Thank you very much, Wendelin. Okay, so I think we managed to finish the proof. And do you guys think it's a good idea for us to write it to reinforce that we actually understand? Let's just write the lemma part. How about that? Okay, we'll not look at the book and we'll just write the proof ourselves. Okay, reproduce the proof. So we prove or should say we use an induction on n. Okay, so base case. N equals 1. N equals 1. So suppose A to B closed interval is a subset of I1. That's it, just one set. Okay, and let's write I1 to be C to D. Okay, let's write I1 to be C to D. Okay, actually, you know what? Let's be rigorous. If the length of I1 is infinite, then there's nothing to be proved. If length of I1 is less than infinite, we can write I1 equals C to D with CD in real and C less than D. This way we have A to B is a subset of the open interval C to D, and this tells us C is less than A, less than B, and is less than D. And this tells us B minus A is less than D minus C. And D minus C is exactly the length of I1. Okay, so as needed. So this proves the statement for n equals 1. So that's the base case. Inductive case, or inductive step. Okay, so suppose for some n greater than 1, suppose we broke the interval into two parts exactly. Yeah. Suppose for some n greater than 1, we have the following. For all pairs of A, B, and real with A less than B, if the closed interval AB is contained by the union of I1 all the way to IN, remember the n is this value, okay? If that's true for open intervals, I1 all the way to IN, then we have B minus A is less than or equal to the sum of the lengths of Lik. So this is the induction hypothesis. So let's mark that as such. So this is our induction hypothesis. So actually, you know what? Let's assume. Okay. So this is our induction hypothesis. Okay. And now we need to show that the implication still works when n is n plus 1. Okay. So now let A to B be arbitrary with A less than B. Okay, and we suppose there exists open intervals I1 all the way to IN plus 1. There exists open intervals such that they covers A to B. Such that A to B is contained in I1 union all the way to IN union IN plus 1. Suppose this is the case, and we need to show B minus A is less than or equal to the sum. This time K goes from 1 to n plus 1. So that's the induction step. Okay, so that's the structure of the induction proof. So you need to show that. Okay. So here, B must belong to one of the intervals I1 all the way to IN plus 1. In base case, Oh, no. Oh, yeah, you're right. Yeah, this is a mistake. Okay, so here this should be a closed interval. My bad. Thank you very much for pointing that out. Yes. So this is just a restatement of closed interval a to b is contained in I1 because we rewrote I1 to be open interval c to d. Yeah, Gwendolyn, you're correct. Thank you very much. So here, let's continue the inductive step. B must belong to one of the intervals I1 all the way to In. Relabel the interval relabel, or should say one of the intervals I1 all the way to relabel one interval that contains B as In plus 1 if necessary. Okay, so basically saying if B is already contained in the last interval, then nothing needs to be done. You don't need the relabeling. But if not, right, you can just pick one interval that contains B and call that In plus 1. Okay, so let's write In plus 1. So once again, you can just say if if the length of In plus 1 is infinite, there's nothing to prove. There's nothing to prove, thus let's write assume In plus 1 has finite length and write In plus 1 to be C to D. To be C to D, okay? Here, as a result, B is greater than C and is less than D. Okay, because In plus 1 contains B. Okay, if C is less than or equal to A, if C is less than or equal to A, then immediately we have B minus A is less than or equal to D minus C, which is the same as, the right hand side is the same as the length of In plus 1. And this is star, okay? And star obviously holds. Because only one term is already greater than the left-hand side, so it's done. And thus, star holds. Thus, we assume A is less than C. Assume A is less than C. So we have this diagram here. A is less than C, is less than D, and is less than, sorry, A is less than C, less than B, which is less than D. So that's the situation here. Here we have the last interval, In plus 1. In plus 1, okay? So now let's consider, we claim that the closed interval A to C is a subset of I1 union all the way to In. Indeed, if x is in A to C, close interval, then if x is in A to C, close interval, we want to show that x is in the right hand side as well, then x is in A to B, and x is not in IM plus 1. Hence, x is the first part, x is in A to B, tells us x is in the union of I1 all the way to IM plus 1. And x is not in IM plus 1. Thus, x is in the union of I1 all the way to IN as claimed. You do the element chasing argument, start from an arbitrary element in the left, and it turned out to be also in the right. So the claim is now shown. So by the induction hypothesis, which is this one, by the induction hypothesis, we have C minus A is less than or equal to the sum of the length of ik, k from 1 to n. So you have that. Okay. And now we can complete the argument. So b minus a, therefore, b minus a is, looking at the picture, is b minus c plus c minus a. Right. So b minus c, this is less than or equal to d minus c. You can see because b is greater than c less than d. b minus c is less than or equal to d minus c. So the first term d minus c is exactly the length of L is the length of IM plus 1. And c minus a is less than or equal to the sum of the first n, the sum of the length of the first n intervals. Okay. So this is the sum of Lik. K ranges from 1 to m plus 1. So that's exactly which is a star. As needed. Okay, so this finished the induction step. So therefore, by the principle of induction, principle of mathematical induction, that's the formal statement that justifies the proof by induction. By the principle of mathematical induction, for all AB in real, A less than B, if for some n equals 1, 2, and so on, A to B closed interval is contained in I1 union all the way to IN, then B minus A is less than or equal to the sum of the lengths of IK, okay, from 1 to n. Okay, this finishes the proof. So that's what we call the lemma. Okay, that's what we call the lemma. So by the lemma, then you can show that the theorem here. Okay, the theorem, the main theorem here says b minus a outer measure equals no, it's nonsense. A to b outer measure is b minus a. That's the theorem. Okay, so let's write that as well. Okay, make sure we understand everything. Okay, so we're going to prove the first direction. Consider the sequence a minus epsilon, a b plus epsilon, empty set, blah blah blah, of open intervals right. It covers a to b, the closed interval, and its total length of the sequence. Compactness is needed to work with finitely many. Yeah. Is b minus a plus 2 epsilon. Therefore, a minus b outer measure is less than or equal to b minus a plus 2 epsilon. Okay, let epsilon be positive. Since epsilon is arbitrary, we have b minus a, we have a, no, this is nonsense. A to b outer interval, not absolute value. Okay, my goodness. Okay, I'm talking about the outer measure of a to b, closed interval. Okay, this direction is very easy. Okay, let's prove the opposite direction. Okay, so let I1 all the way, I2 all the way be a sequence of open intervals with the union of ik, k from 1 to infinity, contains a. Sorry, not contains a, but contains the closed interval a to b. Okay, since a to b is closed and bounded, so we're verifying the assumptions of Heine-Borel theorem. Is bounded and closed. Since this is bounded, closed, and bounded, and ik is open for all k, you have open cover by HB theorem. By HB theorem, there exists a finite subcover And you can just pick the largest index in the finite subcover to be n. There exists n equals 1, 2, and so on, such that the union k goes from 1 to n ik contains a to b. Okay, so that's the key step here. Select a finite subcover is what makes the opposite direction tick. Okay, so and by the lemma, you have b minus a less than or equal to the sum of the length of ik, k from 1 to n, which is of course less than the infinite sum. Okay, and since the I1 all the way to ik is an arbitrary, I1, I2 all the way is an arbitrary cover of open intervals that covers a to b. Take infimum. You got b minus a is less than or equal to the outer measure of a to b. As needed. And this finished the proof. Okay. Okay, so that's pretty cool. Right, so that's a major result, and it's highly non-trivial. Okay, the result above easily implies that the outer measure of each open interval equals its length. Right. So the outer measure of each open interval. Hang on. The result above easily implies that the outer measure of each open interval. Why do you need the result? Why don't we have a to b outer measure equals b minus a immediately? Huh? The result above easily implies that the outer measure of each open interval equals its length. Hang on, why do we need that? Why can't we just say, well, for the open interval a to b, you can pick I1 equals a to b, I2 equals mt, I3 equals mt, and so on. Oh, that's because you only have one direction. That's because you can use this sequence and get this is less than or equal to b minus a. This is less than or equal to b minus a, but what about the other direction? So you can't just use the definition. And I think I actually used this result earlier. I inadvertently used this in my earlier notes, which is not a good idea because you only have that after you prove this result. Hang on, where did I use that? Okay, I remember I used that last time. Yeah, this is where I used it. This is not the definition. So I was trying to give a counterexample that shows outer measure does not satisfy what's called uncountable subadditivity. Okay, remember outer measure satisfies countable additivity here. It does not satisfy uncountable subadditivity. And here I used a counterexample, the open interval 0 to 1, as the union of singleton. And this is, of course, an uncountable collection of uncountable cover, right? So, and it turns out that the left-hand side, 0 to 1, has an outer measure of 1, which needs exercise 6. Actually, the justification is not the definition, but rather exercise 6. Okay, let me just put that here. And on the right, the uncountable sum is defined as the supremum of finite sum turns out to be 0. So that's uncountable subadditivity fails. Okay. So okay, so now we have this result. Why don't we just do an exercise? Okay, let's just immediately look at the exercise because it seems like not a terribly difficult way to prove this. Okay, so let's see the exercise number 6. Okay, we'll come back to the rest of the results in Excel later. So how do we prove that? Okay, exercise number 6, prove that if A, B isn't real and A is less than B, then you have open interval. Open interval, semi-open, semi-closed interval A to B all have the same outer measure. So how do we go about proving that? Remember, we have to use you have to use definitions or proofs, the result or prove earlier. Okay. Because it feels like we're proving something that is extremely obvious, right? But because of the weirdness of the real line, everything needs to be handled extremely carefully. Okay. Anything that is not proved cannot be used. Okay, so let's prove this result. How can we do that? As we mentioned, we already have. Let's just take a look at things one at a time, shall we? So to cover an open interval, can't we not use? We cannot use its total length. I was saying that you can use less than, right? So, but now we need an equality. Okay, so let's start with the first one. Okay, proof. So let's start with the first one. A to B, open interval. Outer measure equals B minus A. So let's prove that. Okay, how do we go about proving that? Well, first let's prove less than or equal, which I already wrote a bit earlier. So you take A to B, empty set, blah, 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 as a sequence of open intervals that covers A to B. Okay. Then, by definition of outer measure, the outer measure of A to B is less than the total sum, which is B minus A. Okay, so that's one direction taken care of. What about the other direction? How do we cook up the greater or equal to? Can we use a squeeze argument again? Can we use a squeeze argument? Wendelin says taking the union, right? You want to have that. Okay, so let's try that. You have consider, yeah, let's consider Wendelin's idea. A to B, this is equals union B, okay? So therefore, the outer measure of A to B, closed interval, is less than or equal to the sum of, less than or equal to the outer measure of A union B, not union, but outer measure of open interval A to B plus the outer measure of singleton. The outer measure of singleton is all 0 because the outer measure of finite size is 0, and this is B minus A as needed. Excellent. This is a 0. Right? So we're done here. Excellent. Thank you very much. Perfect. Okay. No need for a squeeze argument. This is great. This is awesome. Okay. So now let's take a look at the other two. Okay. So I believe we can use the result that we just proved. Okay. For example, let's take a look at the second A to B. Left closed, right open equals B minus A. So start with one direction. Why don't we use monotonicity? Since since A to B, left closed, right open is a subset of the closed interval A to B. Then by monotonicity, we have this. And you're done. So that's one direction done. The other direction, well, why don't we just cook up another union situation? Consider the fact that, well, the closed interval A to B is the union of A to B left closed, right open, union with a singleton B. And then use countable subadditivity, or you just need finite subadditivity. Yeah, countable subadditivity implies finite subadditivity. So we got the outer measure of the closed interval A to B is less than or equal to the outer measure of the left closed, right open interval A to B plus the outer measure of singleton B, which is 0. And the left hand side is B minus A. And that's exactly what we needed. So we're done. And the other direction is similar. And the other relation is similar. So now you have left open, right closed. This is completely similar to the previous one. So we're done. Okay, are we cool? Anyway, so let's come back to the main text and look at the next important result. Actually, you know what? Here we're at this part. The next important result is outer measure is not additive. But let's finish the last section, the last block on the outer measure of A to B. Okay. So, okay. So now we have the previous result has the following important corollary. You may be familiar, dude, this is just an overkill. Just use the fact that the measure is 0 with one element. Dude, is this overkill? Let's think about it. Is this overkill? But because we don't have additivity, right? Mario, right? So this is what I'm trying to get to. You think this is overkill because you say, okay, you just have this, right? And you just take the outer measure on both sides. But the problem is we don't have additivity. Mario, this is not an overkill because you don't have additivity. If you take outer measure on both sides, you don't you don't have equality anymore. Okay. That's the whole point, right? So here we have the next section here. We don't have this. Or you have to use union of infinite set. Why? You don't have to use infinite because countable additivity already implies countable subadditivity implies a finite subadditivity. You don't always use infinite union. It's already implied by that here. Countable subadditivity implies finite subadditivity. We don't have to use unions of infinite sets because you can just take ak equals empty for k greater than n. Okay. Countable subadditivity is stronger than finite subadditivity. And here we're only using finite subadditivity. Okay, let me just emphasize that, okay? Yeah, you can approach it. Yeah, I know you can do that. You can do that. I'm just not bothered. You can approach it by infinite union. Yeah, you're saying that something like this, right? So you have a to b like this. Perhaps you want to do a minus 1 over n, other a plus 1 over n, b minus 1 over n, like this sort of squeezing argument. Is that what we're trying to say? For all n, a to b contains closed interval a plus 1 over b, 1 over n, and b minus 1 over n. That's what you're trying to say. And then use the monotonicity. You have a to b, outer measure greater or equal to the outer measure of the right hand side. The outer measure of the right hand side is a theorem which equals b minus a minus 2 over n. And then you squeeze n to infinity. Right? So that's what you're saying, right? So this also works. It also works because here this part we want the outer measure of the open interval a to b to be greater than b minus a. Right. So that's another way to do that. Okay. Here we use finite subadditivity. You can also use monotonicity and yeah. So basically, Archimedean property is just said 2 over n tends to 0. That's Archimedean property. Yeah, totally. I completely agree. Right. So that's another way. What is not okay, however, is say consider you have this decomposition and then you simply just use additivity, because additivity does not hold. Additivity doesn't work for outer measure. So that's the, the big theorem, right, which we're about to get to. Right. So yeah, both okay. This is okay, this is okay. Thank you very much for raising that point. Okay, but neither of them are overkill. Make sense? Okay, so let's get to the let's continue. Okay, let's continue here with well, we didn't prove. I think it's already 9:11, right? Right now it's already 9:11. We started from 7, and I think I will not cover. Okay, I will not cover the proof of Heine-Borel in the text. Okay, I'll just skip that. I apologize for that, but I do have a video. I do have a video on my channel that proves A to B closed interval is compact. Okay, you can just search compactness on my main channel. Compact on compactness. In the last part of the video, I showed that the closed interval A to B is compact. So which also used the least upper bound property. I didn't have time. I don't have time to look through this in this stream because I really want to get to the fact that outer measures aren't the outer measure isn't additive. Okay, so that's why I'm skipping the proof of Heine-Borel. Additivity doesn't work, dude. Additivity does not work on disjoints. That's the whole point, right? That's the theorem which we're about to get to. Okay, additivity, and actually countable additivity is a property of measure. This is not a measure. This is an outer measure. Okay, as we will get to in future episodes, when outer measure is restricted on a sigma algebra, then it becomes additive. So that becomes a measure. So right now this is not a measure. I was going to say a lot of this reminds me of compactness. Oh shoot! So, Marilla. So apologize for being blunt, but this is really not true. Okay, this does not work for disjoint set. Okay, even though, of course, when we talk about additivity, we always talk about disjoint set, but the whole subtlety is that outer measure does not work. Outer measure isn't additive. So that's the point. But that's okay. That's totally okay because this is highly non-trivial. Like who could expected that, right? So that's why measure theory is hard. That's the whole reason this is a difficult subject because it defies your intuition so much. Okay, outer measure isn't additive. Outer measure isn't additive. So this is one of the reasons why we need to talk about things like sigma algebra. Outer measure, remember, outer measure at this point is defined for all subsets of real. Okay, and it turns out that we have to give up that that generality. Okay, we're not going to discuss measures for all the subsets of real because so many sets of real, so many sets in real are just too weird. Right, and if we insist on discussing measures for all subsets, then weird things happen, like 2.18. Okay, well, we'll get to that. Okay, this is highly non-trivial, and I'm glad that there's discussion over this in chat. Okay, so that's why we'll be here. Okay. Okay. Anyway, here we have a nice little corollary that shows non-trivial intervals are uncountable. Okay, of course, the fact that the non-trivial intervals are uncountable, things like 0 to 1, okay, is uncountable. This can be proved using many ways, such as Cantor's diagonal argument. This is probably familiar in every analysis book, and there's tons of videos about it. The intervals aren't countable. This can be proved in many different ways. But here we're going to use an outer measure argument. Okay. The proof using outer measure that is presented here gives an interesting alternative to Cantor's proof. Let's go. every interval in R that contains at least two distinct elements is uncountable. How do we prove that? Well, it's trivial, because a countable set has outer measure of 0. But here, if we have 2 points that are distinct, a less than b, say, then the outer measure by monotonicity, outer measure of I is greater or equal to b minus a, which is positive, right? But every countable subset has an outer measure of 0, so we're done. Right? That's pretty cool. Okay, next up, outer measure is not additive. Let's go. So we have had several results giving nice properties of outer measure. Now we come to an unpleasant property of outer measure. If outer measure were a perfect way to assign a size as an extension of the length of intervals. By the way, this extension of length, okay, extension of length means the outer measure agrees with the usual length for intervals, right, which is something that we just spend a lot of energy to prove. So 2.14 says the outer measure agrees with the usual length for closed intervals, closed and bounded intervals. And the exercise we just did says, oh, the outer measure agrees with the usual length in all the other intervals as well. So that's an extension. But here we have to discuss something that is rather unpleasant. Right. It says, if outer measure were a perfect way to assign a size as an extension of the length of intervals, then the outer measure of the union of two disjoint sets would equal the sum of the outer measure of the two sets. Right. So this is our dream. Unfortunately, it doesn't work. Sadly, the next result states that the outer measure does not have this property. In the next section, we begin the process of getting around the next result, which will lead us to measures theory. Okay, so now let's take a look at the non-additivity. The statement says there exist disjoint subsets A and B of R such that the outer measure of the union of A and B is not the same as the outer measure of A plus the outer measure of B. All right, so this proof here, as I recall, it will make use of the axiom of choice. Okay, the proof here will make use of the axiom of choice. Basically, you need axiom of choice to construct the disjoint subsets A and B, and we'll see how that's done. Okay, so once again, this is a highly non-trivial result. Proof. Okay, so it says for A in a closed interval minus 1 to 1, let A tilde be the set of numbers in minus 1 to 1 that differs from A by a rational number. Okay, so A tilde is a set. A tilde is a set. If you fix A, for a fixed A, you can define A tilde as a set C in minus 1 to 1 such that A minus C is rational. Right, so we can think of this as an equivalence class here, Axler remarked. Right, because we can say A is equivalent to C if A minus C is rational. And it satisfies three properties of the, measures are defined on sigma algebra, exactly. Measures are defined on sigma algebra. Sigma algebra is a special class of subsets of real. Okay, it doesn't have to be a subset of real, but basically it's a special class of subset. And on that, outer measures well behaved. Okay, that's where I'm giving spoilers, but basically that's what we're going. Okay, so here, essentially what we're doing is we're defining an equivalent class on real. And to verify that, we just need to check three properties. First, you have reflexiveness. A is is equivalent to a itself. And this is obvious because a minus a is 0, a rational number. 2, if a is equivalent to b, then b is equivalent to a. That's the that's the symmetric property of equivalence relation. And this is also obvious because if b is equivalent to b, a is equivalent to b, if a is equivalent to b, then b minus a is rational. Okay, then b minus a obviously being the negative of a minus b. Okay, I'm talking about a minus b. A minus b is rational, then b minus a being the negative of a minus b is also rational. So 2 is true. And lastly, you have if a is equivalent to b and b is equivalent to c, you have a is equivalent to c. Okay, and this is also quite simple because a minus b is rational, b minus c is rational. So a minus c being the sum of a minus b and b minus c is also rational, therefore a and b are equivalent. Okay, so this shows that differ by a rational number is an equivalence relation. And once you have an equivalence relation on any set, okay, for any set, if you have an equivalence relation on it, you can partition the set into equivalence classes. And here, for any real a in minus 1 to 1, for any a in minus 1 to 1, actually here we're talking about the full set being minus 1 to 1, okay? We're not talking about the whole real. But basically, on the set minus 1 to 1, you can impose an equivalence relation. Equivalence relation being two numbers differ by a rational number. And then you can define equivalence classes using that equivalence relation. And A is just a representative, in its own equivalence classes. Of course, there's many representative. Okay, so here we have a tilde. We partition on the random but a fixed length. No, not random. Not random at all. Okay, we partition based on the equivalence relation. Because this is a basic fact from set theory. So here, just to remind ourselves, some set theory. Interlude. Let tilde be an equivalence relation on a set R, on a set S. Okay, we can define this is a notation for the quotient set. The quotient set of equivalent classes according to associated with this is basic set theory. Associated with tilde. Okay, it's associated with tilde. So basically, this is what it means. If and this is what it means. So with tilde. So this is what it means. Every element in S belongs to exactly one equivalence class, okay, the equivalence classes are disjoint are mutually disjoint. If you take any two equivalent classes, they must have zero. It must have no intersection. Are mutually disjoint. That's a partition. Okay, mutually disjoint, and the union of all equivalence classes is S. Okay, so an introductory example of equivalence class would be integer modulo n. So if you think of, say, just take a look at an example. So what we do in basic algebra, integer modulo n. Okay, Zn. So Z, of course, is the set of integers. You can partition Z into equivalence classes based on the remainder they get after divided by n. Pretty much the infinite union of those classes gives you the rationals, and by one, of course, no, the infinite union of all those classes give you the whole minus 1 to 1, not just rationals. Because, as I said, the equivalence classes is a partition on the set, right? So the union must be the whole set, not just the rational. Okay, so let me just finish writing this example. So Zn, n is greater or equal to 1, contains element, usually written this way, 0. These are the integers that are multiples of n. And 1, these are the integers after dividing by n has a remainder of 1, and all the way to n minus 1. Yeah, union of all classes give minus 1 to 1. Here in Excel, we're discussing minus 1 to 1. But it doesn't really matter, okay? The choice of 0 to 1 also works here. You can also construct a you can also construct a non-measurable set, you can construct an example that kind of additivity fails using 0 to 1 as well. Okay, so here we have, so let me just, for example, this is what Z4 looks like. So imagine this is a big pie, and not a number pie, just like a delicious pie, okay? So all the integers are in there. 0 here has 0, 4, 0, 4, minus 4, 8, minus 8, blah, blah, blah. Okay, and 1 contains 1, okay, minus 3, 5, all right, and then 9, minus 7, okay, so this, and so on, okay, and 2 contains what? 2 contains 2, minus 2, 6, minus 6, and 10, and so on. And 3 contains what? 3 contains 3, minus 1, 7, minus 5, and what's that? 11. Yeah, and so on. So this is an example of equivalence class. So this is an interlude, okay, on set theory. Equivalence classes, so you can find it in any proof, introduction to proof book, okay? Like how to prove it, for example. Check out that book. Okay. And my personal favorite, by the way, if you wish to do some warm-up or review on basic proof writing, set theory, and whatnot, check out this book, which I like a lot, called The Tools of Mathematical Reasoning. Unfortunately, it is not free. I usually only do free books, okay, or at least free books that are legal. Okay, I don't want the channel to get demonetized. So basically, that's the cover. What the cover looks like. The Tools of Mathematical Reasoning. It's not a very thick book, and it covers quite a few things. But I'm pretty sure the content is very standard. Basically, any introduction to proof writing book will contain in higher mathematics. Okay, I'm not talking about proofs in Euclidean geometry, but basically any proofs, introduction to proof in higher mathematics will cover basics of set theory. Okay, and actually I make a lot of my quizzes using this book. Okay, it's a good way to review this stuff. Okay. Anyway, so let's come back to the proof. So A tilde is what? A tilde is the set of numbers in real numbers in -1 to 1 that are equivalent to A, where the equivalence relation is defined by differing by a rational number. So that's the equivalence relation. Okay, so how do we construct the subsets A and B in the non-additivity statement? Let's go. If A and B are in -1 to 1 and the are -1 to 1 and their corresponding equivalence classes are is not empty. Hang on. If A and B are in -1 and 1 and they overlap, right? And they overlap, then the two set must be the same. Yeah, exactly. That's just basic set theory, right? As we said earlier, equivalence classes must be disjoint. So if you have an overlap, then if two equivalence classes have overlap, then they must be the same. The two equivalent classes are the same. Right? So this is standard set theory, but Axler, being very nice, actually provided a proof. But I think we can skip that now, right? That's just a basic fact about equivalence classes. Equivalence classes are disjoint. Right? So if you have two equivalent classes that has non-empty overlap, right, non-empty intersection, then that must mean they are two same equivalent classes. So we're going to skip this part. Okay? And now let's take a look at what follows. Right. So here, right, this is, I was saying, like Mario, right? So the union of all the classes gives you the whole set, not just the rationals. A tilde is an equivalence class, right? And you can select, for each number in -1 to 1, it belongs to one equivalence class, one and exactly one equivalence class called A tilde, and you union all of them, you get -1 to 1. Everything in -1 to 1, not just the rationals. Okay, now let's continue. So far, this is, I mean, I don't know who came up with this idea, but I mean, this is highly unnatural. I'll be honest, I don't know how to motivate this step. Okay, perhaps you just have to memorize it. Okay, anyway, let V be a set that contains exactly one element in each of the distinct sets. So you see, here we're using the axiom of choice. What we're saying is, from each equivalence class, we're going to pick one element from it. Right. So basically, that's the crucial step here. Yeah. Let's read that again. Let V be a set that contains exactly one element of each of the distinct sets. Each of the distinct sets A tilde. Remember, as we said, for each little a in -1 to 1, it has an equivalence class. And the way you construct V is as follows. You pick exactly one element from each distinct set. So basically, imagine this is, let's draw a Venn diagram. This is -1 to 1, close interval. And here you have a partition. You cut it into pieces, okay? And from each equivalence class, you pick exactly one. Pick exactly one number and put them together. This is what we call V. Of course, this is highly difficult to visualize, but if you assume axiom of choice, this operation is valid. No, Rolf. Sigma algebra has nothing to do with make things add up to 1. You're talking about probability measure, one of the axioms of probability measure, so we're not even discussing that, okay? Sigma algebra is, we'll get to that, but basically, as a spoiler, is to restrict the classes of sets to which we will assign measure so that the non-additivity disappears. So yeah, so right now outer measure is defined on all subsets, namely the power set of real, which is too large. And if we restrict that to sigma algebra, then non-additivity disappears. So that's it, okay? Okay, so it has nothing to do with normalization, okay? Anyway, so let's continue. Here we have this weird set V, which is extremely difficult to visualize. But if you assume axiom of choice, this is certainly valid. In other words, for every little a in -1 to 1, the set V intersect A tilde has exactly one element. Exactly. For every a in -1 to 1, you're going to look for its equivalence class. And V only contains one element in that equivalence class. And this is true for every little a. So this is V, which is extremely difficult to visualize. All right, so now what's going on? Let R1, R2, and so on be a sequence of distinct rational numbers such that R1 and R2 enumerates, basically. So that's -2 to 2. That's -2 to 2 intersect with Q. The left-hand side consists of all the rationals in -2 to 2. What we're saying is we're going to enumerate all of them as a sequence. This is, of course, doable because rationals are countable. All right. Okay, so this is nice. Then we have what? Then it claims -1 to 1, -1 to 1, the whole closed interval, -1 to 1, is the union of Rk plus V. By the way, Rk plus V, this is the translation. Remember, we defined that operation earlier, T plus A, where T is a number, T is a real number, A is a set. This is defined as the set of numbers of the form T plus little a, where little a is in big A. So here you're just shifting V by Rk. Shifting V. So here V is this weird set. Okay, and then you're going to look at shifted versions of V. Shifted by how much? Shifted by Rk. Shifted by all the possible Rk. So you can shift V by R1, shift V by R2, blah, 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 and then you take the union of all those shifted versions of V. And here it claims that -1 to 1 is a subset of that union. Okay, once again, this is extremely difficult to visualize, but let's just see why this inclusion is true. Where the set inclusion above holds, okay, because let's use the usual element chasing argument. Let A be in -1 to 1. This is an arbitrary element in the left-hand side. We want to show this is also in the right-hand side. Yeah. Okay, -1 to 1. -1 to 1, that's A. A is in -1 to 1. And let V be the unique element. That be the unique element of V intersect A tilde. Right? So basically, that's the unique element in V that is equivalent to A. Yeah, this is exactly Vitaly said. Exactly. You're completely right. This is Vitaly said. Yeah. So we're letting V to be the unique element in big V that is equivalent to A. So A minus V is in Q. So A minus V is in Q, but remember, V is little v. Little v is also in -1 to 1. Little v is also in -1 to 1 because here, v is a subset of -1 to 1, and the difference between A and V is between -2 and 2. So that's why we're considering -2 and 2. Yeah, it is called Vitaly set. It is called Vitaly set. So, which implies, so A minus V is in Q, but that difference, as I said, is in -2 to 2, which is also rational. So it has to be one of the RKs. So it has to be one of the RKs. So rearranging, you get A is RK plus V. A equals RK plus V. That's exactly, RK plus V is exactly an element in RK plus big V. RK plus little v is an element in RK plus big V, by the definition of translation. So little a belongs to RK plus K, RK plus V for some K in the set of positive integers, and therefore A belongs to the union of RK plus K, and where the union is over K. Right, so here you have that. Okay, you now have what? You now have a containment relation. So let's use the property for outer measure, namely monotonicity. The inclusion above, the order preserving property, aka what I call monotonicity of outer measure, and the countable subadditivity, use the countable subadditivity on the right, gives you what? Well, this is, first of all, you take the outer measure, you get an inequality. And then you use the subadditivity, you get the summation. And let's not forget, you also have translation invariance. You also have translation invariance, so the right-hand side is just the sum of the outer measure V. Okay, so that means the set V, the set V must have an outer measure that is positive. Okay, so we have managed to show that this V that we defined earlier has an outer measure that is positive. Okay, so it might seem a little bit of a weird situation, but basically what we're still trying to get to one thing. Okay, the main result says there exists disjoint subset A and B such that additivity fails. We still haven't touched on how to define A and B. But right now what we have done is that we constructed a weird set V, which is extremely difficult to visualize, that somehow has an outer measure. Hang on, what's going on? No. An outer measure that is positive. Yeah, that is positive. So if V outer measure is 0, then the sum would be 0, right? So it has to be positive, or at least greater than 0. It has to be positive. Yeah, it cannot be 0. That's what it means. So it's non-zero. All right, so note that the sets R1 plus V, R2 plus V, blah, 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 and are disjoint. So basically, here you have a disjoint union. Let's just see why they are disjoint. So suppose there exists, they have non-empty intersections. So suppose you have two of those sets, Rij plus V and Rj plus V and Rk plus V, that aren't disjoint. Okay, suppose there is a common element, say T. Then you would have T equals Rj plus V1 equals Rk plus V2. And then you rearrange, you get V1 minus V2 equals Rk minus Rj, which is in Q. But the problem is V1 and V2 are supposed to be in different equivalence classes. Right? V1 and V2 must come from different equivalent classes by the construction of V. But here you have V1 and V2 being the same. Okay, so here you have V1 and V2 being the same, exactly. By the uniqueness of the choice from each equivalence class. So V1 V2 must be the same, so Rj and Rk are the same, which implies J and K are the same. Remember, Rk is an enumeration. So that's the enumeration of rationals in -2 to 2. So if two sequence values are different, then this index must be different. Okay, it's injective function. Okay, so here we have R1 plus V, R2 plus V, blah, 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 are disjoint. Nice. Nice. Okay, so now we have the union is a subset of -3 to 3. Right, this is correct because each RK belongs to -2 and 2. And everything in V is in -1 to 1. So adding everything adding everything arbitrarily, right, you would still be in -3 and 3. Okay, this is in -3 and 3. That's cool. The set inclusion implies the following. Okay, so you have another inclusion. Nice. And then you use what? And then you use, hang on. Oh, here, by the way, this is not an infinite union. This is a finite union. This is a finite union. So you pick an arbitrary little n. Pick an arbitrary little n. And here what we have is here we have the sum of Rk plus V, outer measure, using translation invariance. This gives you simply n copies of the outer measure of V, which is n times V outer measure. Okay, so the outer measure of the union, why is it strictly less than, huh? Why is it strictly less than? Why is it strictly less than? So 2.19 is this one. Here it says 2.19 and 2.20 suggests that we choose n such that nv outer measure greater than 0. Greater than 6. Okay, greater than 6. Okay, so if we do that, if we choose n to be that, yeah, because as we said here, if we pick n so that n outer measure v is greater than 6, you would have, yeah, you use transitivity. That's the sum of k from 1 to n, rk plus v, outer measure. So this is where the strict inequality comes from. Use transitivity. Okay, and what else? If we have equal, oh, okay, so it didn't actually construct A and B, but we're using a contradiction argument. If we had A union B outer measure equals A union B, equals A outer measure plus B outer measure for all disjoint subsets, then by induction you would have finite additivity as well. Yeah, that's true. However, 2.11 tells us no such result holds, right? Because this contradicts this. 2.21, 2.21 contradicts that because RK plus V, as we argued, they're all disjoint, but here you have a strictly less than relation. Okay, so therefore there exists. It did not um, define A and B explicitly, but rather relied on a contradiction. However, the construction of V is crucial. Right? The construction of V, which relies on the axiom of choice, is crucial here. Okay, so this proof, of course, is highly elaborate and highly non-trivial. Let's see what Axler has to comment on that. So subadditivity forces the strict inequality. Well, subadditivity itself does not force strict inequality. Subadditivity is something that is true in general, right? That is true in general. It's pretty harmless, but it's rather because of the fact that you have subsets of real that are like V. Okay, this is something what we call non-measurable sets. The existence of non-measurable sets destroys additivity in general. Yeah, it is a bit of headache inducing. That's exactly. This is absolute torture, mental gymnastic. I know, but this specific proof exactly. Right. But if you can follow it and preferably reproduce it, then I think um, you can appreciate why the measure theory is so difficult. Because I mean, this is not a unique experience to you. This is something that well, even the top tier mathematician in the 20th century, in the beginning of the 20th century, struggled with this. Anyway, so hang on, guys. I just need to reply to a message, and I'll come back in like 2 minutes. I just got to reply to this message real quick. Okay. Yeah, well, I think here this set V, the Vitali set, right? That's probably the reason why it's denoted as V. V is dense in -1, huh? I think you can choose elements in V in such a way that this is dense. And the reason and the way you do that should be quite straightforward as well. Hang on. You can. I think you can show that the Vitali set is dense. Honestly, I will have to review this last proof again tomorrow. It's 4 a.m. here, time to sleep. Yeah, yeah. Thank you very much, Wendlin, for joining the stream. I think Vitali set is dense. Although that's not really the point here, right? Actually, it's not tomorrow. It's Saturday. Mathematical finance. And the Sunday stream is, I will post the announcement soon, is rescheduled to Saturday evening. Sunday stream is rescheduled to Saturday evening because I have things this week on Sunday evening. Okay, so yeah, this is the proof, which is very non-trivial, but okay, we'll reproduce that. After that, we'll look at some examples and perhaps look at sigma algebra. Okay, the axiom of choice, which belongs to set theory, states that if epsilon is a set whose elements are disjoint non-empty sets, then there exists a set V that contains exactly one element in each set that is an element of big epsilon. Non-measurable set means no meaningful measure. You're right. You're right. So, Rolf, non-measurable set, the notion of non-measurable set means the following. We wish to define the size of, we wish to define the notion of measure, right? That's basically the notion of size for subsets of real. And we wish that the notion of measure behave in a certain way. We wish to have that to behave in a certain way. However, if we include all the subsets of real, then the properties that we desire becomes mutually contradictory. Okay, so that's the problem here. Right? We want our measure to behave in certain ways that are intuitive. But if we decide to include, if we decide to assign all subsets a measure, then those desirable properties becomes mutually contradictory. That's why we decided to restrict the classes of subsets to which we assign measure. And everything else is called non-measurable set. It's just a requirement of internal consistency. It's not, there's nothing intrinsic say, oh, a set cannot be defined as a measure. It's that if we include those sets, then the function itself will have problem. Okay. All right. Hang on. Let me just. Kind of weird, exactly. It is very, very weird. It is just extremely counterintuitive. So that's why you see the notion of axiom of choice is controversial. Right? A small minority of mathematicians object to the use of axiom of choice. Thus, we will keep track of where we needed to use it. I have to process it. Thanks. No worries. Actually, you know what? Why don't we get to the sigma algebra part? So this way, it's easier for you to process that. Okay. I will I will defer the reproduction of this proof. I will defer the reproduction of this proof and in our own language, but let's just for the rest of the stream, we will look at measurable spaces and functions, the notion of sigma algebra. How about that? Now, because the details of this big proof is rarely encountered in future. Okay, even though this proof is rather ingenious, the detail of this construction does not really matter. Okay, you can just live with the high level knowledge that okay, there exist disjoint subsets A and B of R such that additivity fails. And with that in mind, let's get into the next section. Okay. All right. So here, measurable spaces and functions. The last result in the previous section showed that outer measure is not additive. Could this disappointing result perhaps be fixed by using some notion other than outer measure for the size of a subset R? Right? We picked the outer measure. We picked the definition of outer measure, which is a specific way to assign sizes to subsets of R. Perhaps that's not a good notion. Perhaps there's something wrong with outer measure. Perhaps there's a better choice. However, the next result answered this question by showing that there does not exist a notion of size called the Greek letter mu in the result above that has all the desirable properties. Okay, so this is a rather disappointing situation. It's not a fact that it's not because we aren't smart enough, okay, to define sizes appropriately. This is not our fault. Okay, it's simply because to have all the desired properties, it just does not exist. Okay, your wish list of axioms are mutually contradictory. Let's see. Property C in the result below is called countable additivity. Countable additivity is a highly desirable property because we want to be able to prove theorems about limits, the heart of analysis, which requires countable additivity. Okay, so here's the big theorem. Non-existence of extension of length to all subsets of real. Let's go. There does not exist a function mu with all the following properties. Okay, this does not exist. What are the properties? First, mu is a function from the set of subsets of real. Basically, mu is you can write it this way, as in on a power function. So power set. The set of all subsets of real is denoted as power set p omega. So PR, okay, not omega, PR. The power set of real is the set of all subsets of real. So mu is from the power set to 0 to infinity. Okay, extended version. And also you have this extension property. Mu I equals the length of I for every open interval. Right, so this is the baseline expectation. It has to agree with the usual length. Otherwise, it's not extension, right? C, that's countable additivity. That's countable additivity. So here we have the notion of countable additivity, which will be a property of measure, but not a property of outer measure, because outer measure is defined for all subsets of real. Right, so here, mu of the union of AK. Okay, AK is a countable family. Countable family of disjoint subsets is equal to the sum of mu AK. Okay, so that's nice. We want that. And D is translational invariance. Okay, so they all seem rather innocent. So basically you want these properties to hold, but unfortunately they are mutually contradictory. Okay, so let's see the proof. Actually, you know what? The proof, let's skip that proof, but let's just take a look at sigma algebra. Okay, let's first take a look at things at a high level. But basically, what this result says, you have to give up something. You have to give up something. A, B, C, D are mutually contradictory, so you have to give up something. Right? Because there's a contradiction, by the way. The proof is a proof by contradiction. Suppose such mu exists and eventually derive a contradiction. So where's the contradiction? Repeating the proof of 2.18, we see that there exists disjoint subsets, blah, blah, blah. So the countable additivity fails. The contradiction completes the proof. So that's why. These properties are mutually contradictory, so you have to give up something. B is non-negotiable. You don't want to mess with B, right? Because if mu I is not even the length for open intervals, then this notion of mu is useless. As I said, C is highly desirable, so you don't want to mess with C either. If you mess with D, then it will be very weird as well, right? If you just shift a set by a distance, then the size changes. That's too pathological. So we're left with choice A, and that's exactly where we're going to design our notion. Okay, so that's why we wish to give up the aspiration of defining sizes for all subsets of R. Okay, so let's continue. Okay, once again, I'm not going over the proof yet. Okay, I just wanted to keep things on the big picture. So this is why the notion of sigma algebra is introduced. The last result shows that we need to give up one of the desirable properties in our goal of extending the notion of size from intervals to more general subsets of R. We cannot give up B because the size of an interval needs to be its length. We cannot give up C because countable additivity is needed to prove theorems about limits. We cannot give up D because the size that is not a translational invariant does not satisfy our intuition of size as a generalization of length. Thus, we are forced to relax the requirement in A that the size is defined for all subsets of real. Experience shows that to have viable theory that allows for taking limits, the collection of subsets for which the size is defined, should be closed under complementation and closed under countable union. Thus, we make the following definition. Okay, so I guess this sentence perhaps is not super convincing. Okay, what experience, right? It's not clear. So basically, this is a little bit contrived, perhaps. The definition of sigma algebra says the following. This is a little bit contrived, but we will see why this pays off shortly. Once again, we're focusing things on the high level here. So, as we mentioned, the original aspiration is to define mu on power set, the set of all subsets, and that's too ambitious. Right? So here we try to restrict that by introducing the notion of sigma algebra. So basically, measures are only defined over sigma algebras. Okay, what's the sigma algebra then? Suppose X is a set and S, scripted S, is a subset of X. Is a set of subsets or a collection of subsets, scripted S. Scripted S is called a sigma algebra on X if the following three conditions are satisfied. First, you have empty set is in S. Okay? Empty set is in S, that tells us immediately that S cannot be an empty collection. Okay? Sigma algebra cannot be empty. It must at least contain the empty set. Next up, if E is in S, then X minus set minus E, or the complement of E is in S. So 1, 2 together tells us that X itself is in S, right? Because X itself is the complement of the empty set. So 1, 2 immediately tells us that both X and the empty set has to be in S. It must have at least 2 elements. Lastly, if you have a sequence of elements, if you have a sequence of elements of S, so these are all elements in S. This is a countable collection. It's a countable collection of subsets in S. Okay, it's countable collection of subsets that are in S. Then their union is also in S. So that's closure under countable unions. Okay, that's the definition of sigma algebra. And we can see from this definition, you have two extremes. First of all, the smallest possible sigma algebra is just the empty set and X. That's the smallest sigma algebra, also called the trivial sigma algebra. This is the smallest sigma algebra possible. Okay. Whenever we define a notion, we always wish to check the trivial cases. Like in linear algebra, when we define the notion of a vector space, the smallest vector space is just 0. That's a vector space. Here, when we define sigma algebra, the smallest possible sigma algebra, given a set X, is just the empty set and X itself. What's the largest possible sigma algebra? Well, the largest possible sigma algebra is just the power set. Because the power set is the collection of all subsets. It satisfies all 3 bullet points trivially. So you have two extremes. The trivial sigma algebra, and which is the smallest, and the largest sigma algebra. Right? The two are the extreme scenario. And usually what we're interested in is somewhere in the middle. Okay, we don't want the biggest sigma algebra because of this theorem, 2.22, and of course we aren't super interested in the trivial sigma algebra, except deliberately looking for counterexamples. Right? So typically, what's interesting is what happens in the middle. The sigma algebra that is bigger than the trivial sigma algebra and is smaller than the power set. Okay. So that's a definition of sigma algebra. And I think there should be a result that tells us the outer measure on the Barreal sigma algebra gives you what you wanted at the countable additivity. Okay, let me just scroll to that. Okay, so we're getting a little bit ahead of ourselves, of course. Okay, so this is why, because it's easier to see the trees and not the forest. So I'm getting ahead of ourselves just for that purpose. Okay, so where do we have that result? Hang on. All the way down here, huh? A big measure. Yeah, so that's eventually what we're getting to. Additivity of outer measure on Barreal set, right? We've spent a lot of time on outer measure. Barreal sets is a special kind of sigma algebra. So if we give up defining mu from the power set of real to 0 to infinity, so if we give that up, okay, instead we replace the power set by Barreal subset, which is a sigma algebra. then suddenly you have additivity, countable additivity. Okay? And suddenly you have countable additivity and everything works out. Okay, so hang on, well, where do we have that statement? You have additivity of outer measure if one of the set is a Barreal set. Barreal set is a member in the Barreal sigma algebra. Okay, and more outer measure is a measure on Barreal sets. So you have to be a measure, you need to have countable additivity. That's all the way down to 2.68. Okay, so is that gives us a bit clear, tells us what we're going. Okay, did everyone just left? Okay, sorry, I know this is perhaps a little bit getting ahead of ourselves. Okay, but anyway, that's the motivation for introducing the sigma algebra, right? Right. We saw that outer measure is not additive, a major setback. And the reason is not because outer measure is not defined, just soaking in it right now. Yeah, I know. It's very dense, right? It's very intense. So the outer measure does not satisfy additivity, something we just shown, right? But that's not the problem. That's not a defect of the definition of outer measure. Okay, so it's not because we weren't smart enough, okay, to to define the notion of size, but because such a notion simply does not exist. So we have to give up something in our desired properties, and it turns out that choosing A, weakening A is the right choice. Weakening A is the right choice, and the set of all subsets is now relaxed to sigma algebra. And it turns out that if you replace the power set by sigma algebra, then suddenly A, B, C, D are compatible. Okay, so that's where we're going. Of course, there's tons of details to verify. Okay. Okay, so that's why. I mean, this is not a critique of other content. Okay, this is absolutely not. But just I'm a little bit suspicious of saying about videos or just tutorials on a quick introduction to measure theory or something like measure theory in an hour or something like that. I'm highly suspicious of I mean, not suspicious, but rather suspicious about the effectiveness, because there's, you see, this is something that is, it takes us a lot of time to really internalize what is going on, even on a high level, right? Even on a high level, right? So we still have a lot of proof that we have not yet covered. But basically, if you want to know why we are interested in notion of sigma algebra, that's basically the reason. The original motivation, the natural motivation, is to define a notion of size that satisfies A, B, C, D. But it turns out that they are mutually contradictory. So what should we do? Well, we decide to weaken one of them. And because B, C, and D are too good to give up, we give up A. Okay, and replace the power set by sigma algebra. Okay, so with that out of the way, let's take a look at the proof of 2.22. Non-existence. Non-existence of extension of length to all subsets of real. Okay. So suppose there exists a function mu with all the properties listed in the statement of this result. Suppose that. Okay, suppose that. And then we wish to derive a contradiction. Here, so we will show that mu has all the properties of outer measurable used in the proof of 2.18. What's 2.18? Well, 2.18 is the non-additivity of outer measure, right? That's 2.18. Yeah, that's 2.18. Okay, so let's continue and see like what's wrong with this mu. Like supposedly we have this mu and see what's going on. Okay, first we have mu empty equals 0, which comes from part B. Right. If A is a subset of B and B is a subset of real, right, then you should have mu A is less than or equal to mu B. And this is a consequence of C. This is a consequence of C because you can construct a sequence of disjoint union. So imagine this is A, Venn diagram, then this is B. You're going to construct a sequence that is A, B minus A, set minus B minus A, and empty sets all the way. So that's a disjoint sequence. So mu B by countable additivity is mu A plus mu B minus A plus a bunch of zeros. Okay, which is mu A plus mu of B minus A, which is of course greater or equal to mu A. Right? We mentioned that mu takes non-negative values, so this is non-negative. Okay, so therefore we have monotonicity as a consequence of subadditivity. Sorry, additivity, countable additivity. Okay, if A, B are in real with A less than B. Okay, so what we have here, we have the open interval A to B is a subset of the closed interval A to B, which is the closed interval of A to B is a subset of A minus epsilon to A plus epsilon, B plus epsilon. So that's the inclusion here. And using monotonicity or order preserving property per Axler, we have what? We have, well, the mu of A to B. Mu of A to B is just B minus A by part B. This is the left-hand side. Okay, in the middle is just mu of the closed interval A to B. And on the right, once again, that's an open interval, so that's B minus A, B minus A plus 2 epsilon. And this is true for every epsilon positive. So therefore, use the squeeze argument, you must have the closed interval A to B to have mu value equals B minus A. So you see how we're doing so. What we're doing so far is a little bit different, right? Say to how we did the proof that the outer measure of A to B is B minus A. So here we are only using the axioms of mu. So these are the axioms of mu which we proposed. And following these axioms, you must have the mu of the closed interval A to B equals B minus A. So far we have no idea about the details of mu. We don't know how exactly mu is defined, but we just know the properties. In the previous section on outer measure is defined explicitly. Outer measure is defined as, well, the infimum of the total length of open intervals that covers A, right? So we have a concrete definition there. Here we don't have one. Here we're just giving out the abstract axioms. We don't know exactly how mu is computed, but if we assume these axioms, you must have mu of closed interval A to B equals B minus A. Different approaches. Okay, and now let's continue. Suppose you have a sequence of subsets. Suppose you have a sequence of subsets of real. Then you can construct a disjoint sequence. How? Well, you can start with A1 and the second set being A2 minus A1. So obviously the first two are disjoint. Right? Obviously the first two are disjoint, and then you do A3 minus A1 union A2. Right? So A1 union A2 contains everything in A and everything in A1 and everything in A2. So A3 minus those things tells us the third set. That tells us the third set is disjoint with both A1 and A2 minus A1. Okay, so you can repeat this. And by the way, by repeating this, can we write the fourth one? What's the fourth one? Well, the fourth one is obviously A4 minus A1 union A2 union A3. And you can keep doing this forever. So you get a disjoint sequence of subsets. Right? So this way, you manage to write the union of AK, which is not a disjoint union. You can write a arbitrary countable union into a disjoint union, into a countable disjoint union. And now you can use the countable additivity. So it becomes mu of A1 plus mu of A2 minus A1 plus mu of A3 minus A1 union A2, blah, blah, blah. And what now? And what now? Well, this is less than or equal to mu of AK. Mu of AK. Because, well, A2 minus A1 is contained in A2. Right? So the second term is less than or equal to mu of A2. Use the order preserving property. The third one, this is less than or equal to mu of A3, since it's a subset of A3, and so on. So together you have the sum of mu of AK. Right? So you have that, and what's the problem here? What is the problem here? So overall, this inequality mu of the union of AK less than or equal to the sum of mu of AK says if you have any sequence, right? Any sequence, they may have overlaps. The union will have a mu value, right, that is less than or equal to the sum of all the mu values of AK. Okay, so we have shown that mu has all the properties of outer measure that used in the proof of 2.18, right? So in 2.18, what did we use? In 2.18, what did we use? 2.18 relies on a few ingredients here. 2.18 relies on a few crucial properties. Where did we use those properties? Not in this page. Not in this page. Here we're defining V. We're still not using any properties of outer measure. Where did we use the property of outer measure? Here. Order preserving property. This is order preserving property. So we have the order preserving property used in 2.18. And we also use the countable additivity. Right? Here we use the countable additivity as well as translational invariance. So the point is you can repeat this proof because here we're at this point in the main thing about 2.18 is that we aren't using the original definition of the outer measure. We're only using the property of outer measure. So the 2.18 holds as long as the outer measure property holds. And here we just proved that this mu in 2.22 satisfy all the properties of outer measure. So you can do the same business, okay, pick the same Vitali subset, pick the same Vitali subset and say, okay, well, actually additivity failed, which contradicts subadditivity, because it contradicts part C. So we have shown that mu has all the properties of outer measure that we'll use in the proof of 2.18. Repeating the proof of 2.18, we see that there exist disjoint subsets AB of real, right, such that the mu of A union B not equal to mu A plus mu B. Right. Remember, the whole reason we can recycle 2.18, the proof of 2.18 is because even though 2.18 only talks about outer measure. We aren't using the literal definition of outer measure. We're using the property of it, right? The proof of 2.18 holds as long as the properties of outer measure holds. Countable additivity, countable subadditivity, countable subadditivity, monotonicity, and translation invariance. So those are the only things we need to get a contradiction. So therefore, repeating the proof of 2.18, we see that there exists disjoint subsets A, B of real, such that mu of A union B not equal to mu A plus mu B. Thus, the disjoint sequence A, B, empty, blah, 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 does not satisfy countable additivity. And this is a contradiction. This contradicts C. So it completes the proof. Okay, so 2.22 is a small extension of 2.18. Right? So this is basically a very deep result. This is highly non-trivial. And once again, we remark that this relies on assuming the axiom of choice. Assuming the axiom of choice, you have a you break the internal consistency among the desired properties. Okay, there's that. Okay, so now we're ready to turn to the notion of sigma algebra. Right? And I reiterate that by weakening property A, to be only defined on sigma algebra, ABCD will turn out to be consistent. So that's what we're going. Okay, so now we're just going to focus on just sigma algebra. Okay, so sigma algebra. Okay, so we already read that part. Sigma algebra definition, we already read that part as well. Why don't we just start a new note? Why don't we start a new note and can we do that? Yeah. So sigma algebra. Definition. Let X be a set Can you guys hear my cat? Come on, shut up. A sigma algebra scripted S is a collection of subsets of X with the following property. Okay, one, empty set is always in S. Two, closed under complementation. So what's the notion of complementation? What's the notation? Okay, X minus E, sure. If E is in S, X minus E is in S as well, scripted S as well. 3. If E1, E2, blah, 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 are in S, then the union of EK, K from 1 to infinity, is in S. So that's the definition. So that's the definition of sigma algebra. Let's continue. Of course, this needs to be internalized, not just memorized. Okay. It's probably worth mentioning that in probability theory, elements of sigma algebras are called events. Okay, so in elementary probability theory, we simply say an event is a subset of the sample space. In elementary probability, you have big omega. Right? Big omega, that's the sample space. Each element in the sample space is called an outcome. It's called an outcome. Okay? And in elementary probability theory, we simply say an event is a subset of the sample space. However, in measures theoretic probability, this actually there needs to be some technical requirements. Basically, events are elements in sigma algebra. So the three axioms of sigma algebra states the following. The empty set is an event. The empty set is an event. Basically, you can consider empty set, you can interpret that as the impossible event. Empty set is an event. And if E is an event, then the opposite of E is also an event. Okay, if E is an event, yeah, event is a collection of outcomes. If E is an event, then E does not happen, is also an event. And the third property reads, if you have a countable collection of events, at least one of them occur is also an event. The union has a probabilistic meaning. Okay, if you have, remember in probability theory, A union B. If you have two events, A union B means either A happens or either A and B has at least one true, right? So that's the interpretation of union, probabilistically. So if you have a sequence of events, then at least one of those events occur is also an event. So that's the definition of sigma algebra restated in probabilistic language. Because I know a lot of you are tuning into the stream because you probably aren't interested in measures theory per se, but rather measures theoretic probability, right? The notion of event is only given in the last chapter. Because this is a traditional, Axler's book is a rather traditional measures theoretic book. There's nothing wrong with that. But you don't need to get through everything before the last chapter to study the last chapter. It was just a side comment there. Okay, so it's once you studied chapter 2 and 3, measures and integration, you can read probability and measure pretty well. Of course, there are some caveat. Okay, so there are some caveat, but basically, you can restate pretty much all the results and definitions in chapter 2 and 3 in probabilistic language. Well, what we just said, X, the set X here in probability theory is called the sample space. Right? The elements in scripted S are called events. Right? Integration, the measure in probability theory, that's just the probability measure. Integration in probability theory is the expectation. This is the expectation operator, integration. Okay, so those results can be restated in probability language without having to do extra proofs. Okay, so that's quite nice. Let's continue. Make sure you verify that the examples in all 3 bullet points below are indeed sigma algebra. Well, let's do that. The verification is obvious for the 2 bullet points. For the 3rd bullet point, you need to use the result that countable unions of countable sets is countable. The exercise contains some additional examples of sigma algebra. Okay, so let's continue. Let's verify that because this is important. Remember, Axler said very clearly in the preface, it says, when you encounter the phrase, as you should verify, you should indeed do the verification, which usually requires some writing on your part. Okay, so let's do that. We'll be very faithful and do our jobs. Okay, so here, examples. Example one. Example one. So you have let X be a set. Empty X is a sigma algebra. Okay, let's verify that. Okay, one obviously holds. One obvious, and two, well, because you only have two elements, that's very easy. So, well, if E is empty, then the complement of E, well, is just X. Obviously, this is in zero, in empty and X. If X is if E is X, then X minus X is empty, which is in empty and X. Easy. Three. Well, we can just do a little table here. The union of empty and empty is empty. Union of empty and X is X. And in fact, everything is X. Right, so we have this little table. And then we say, so suppose EI is in scripted S for I in 1, 2, and so on. Then EI is either empty or X. But as we can see, the union will always produce either empty or X. It cannot produce anything else. So 3 is also verified. This is example 1. All right, example 2. Suppose X is a set, then clearly the set of all subsets of X, namely the power set, is a sigma algebra. Okay, so let's write that. Example 2. The power set scripted P of X, which is defined as E such that E is a subset of X. Right, this is a sigma algebra. Another trivial example. Well, one is obvious because empty set is in the scripted P. Empty set obviously is in the power set since the empty set is contained in X. 2. Well, suppose E is in the power set of X, then E is a subset of X, then X minus E is a subset of X, i.e. X minus E is in the power set of X. Right, once again, very easy. 3. Okay, so 3. Suppose you have a sequence E1 blah 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 in scripted P. But so then, well, the union of of EI, obviously this is a subset of X, because everything in the union of EI belongs to X, right? So the union of EI is obviously a subset of X. So then union of EI is in scripted P. Okay, so therefore we're done here. So these are very simple examples. Example 3. Suppose X is a set, then the set of all subset X, then the set of all subset of X such that E is countable, or X minus E is countable, is a sigma algebra. The sigma algebra. So it says here we need to use a result, that the countable union of countable sets is countable. And the way we do that is use a diagonal element. So you can construct a double sequence into a single index sequence. Okay, let's do that. So what's the requirement here? Example 3. Example 3. So let's use the notation S. S is E subset in X such that E is countable, or X minus E is countable. So that's the definition of S here. Okay, so let's start. 1. Is the empty set here? Well, empty set is in essence, the cardinality of empty set is 0. And by the way, countable, I think it should be at most countable, huh? So 0 is, the empty set is considered as a countable set. I think it should be at most countable. So it includes finite set, okay? I think there is let me just check Baby Rudin real quick. What's the definition of countable? So in some book, countable sets refer to countable infinite set, okay? And countable sets together with finite sets together are called denumerable set. I don't know what definition Axler is using, but before I check the supplement, I will look at the Baby Rudin. Countable set. I mean, I can't show it on screen, but I'll just find the definition and I put it in my note here. So in Baby Rudin, countable sets are defined as sets that are equinumerous with the set of positive integers. So in Baby Rudin, countable sets are infinite. And Baby Rudin defined, in Baby Rudin it is defined that A is at most countable if A is finite or countable. That's why I have this notion in my mind. So basically, here I think Axler is talking about at most countable. Yeah, I think nowadays it's more common because it's just because they are literally, right? Yeah. Yeah. So let's treat this as at most countable, okay? So let's just see, put a remark here. So countable means equinumerous with n the set of natural numbers, or 1, 2, all the way to little n for some little n in big N. Actually, it has to be 0. 0 must be in there as well, because this way you include the empty set, which is needed for 1. Oh, can you hear the cat? Oh, I'll play with him a bit shortly. So because of the cat, I might need to stop at 11. Sorry, guys. There are just more important things in life. Okay, so here we have this definition of accountability. Actually, you know what? Why don't we check Axler's own? Is it in the book or in the supplement? Index, countable, C. O. U. Countable additivity, okay, not countable per se. Okay, so let me just get to, I'll try to find a, let me just check Axler's own supplement, which is also in the website. Do we have accountability? Is there an index for the? No, there isn't. Okay, let me just search countable. It says. Countable. It says C is countable. Ah, okay, okay. So you see? Yeah. Vernon is totally correct. Countable nowadays include finite set. The set C is countable if C is empty, or C is C1. Yeah, C can be written as a sequence. You can list them basically. Yeah. Okay. So we're cool. Every finite set is countable. Yeah. So we're good. All right. Okay. So 1, indeed, empty set is a countable set. 2, if suppose suppose X is in, suppose E is in scripted S. Then you have 2 cases. Right? Consider 2 cases. And by the way, what did we say about 2 cases? In one of the streams, perhaps not in the measure theory stream, we said whenever you have to write proof by cases, you got to make sure that the cases are mutually exclusive. And of course, they encapsulate all possibilities. Okay, case 1, E is countable. When E is countable, well, immediately, hang on, if E is countable, can we say XE? Yeah, if E is countable, X minus E, this means X minus E. The complement of the complement, which is equals E, right? Is equals E, is countable. So if you see the definition, if X minus something is countable, that something is in E, is in S. Okay, X minus E is in S. That's case 1. Case 2, E is uncountable. You don't say case 1, E is countable, case 2, X minus E is countable. No. You got to make sure the two cases are mutually exclusive. This is just a requirement in proof writing. We make sure the cases are mutually exclusive and they exhaust all possibilities. Make sure the cases don't have overlaps. Because it is possible that both E is countable and X minus E is countable. Right? Those two are not mutually exclusive. But now we have the cases are actually mutually exclusive. Right? X is countable and X is uncountable. Since since E is in S and E is uncountable, right? This means E is not countable. Right? E is not countable. This must mean X minus E is countable. Okay. X minus E is countable. That means what? This means the countable of this means the complement E is uncountable. Because we need X minus E in S. X minus E is, oh, okay, you already have it. X minus E is countable. Countable sets are in S. So you're done. So that's the two cases. Point 3. So now you have, suppose you have E1, E2, all the way in scripted S. Okay? You need to show the union of all of those E's are still in S. And here let's just use a fact that, which I believe I put a quiz in my community tab before, countable unions of countable sets are countable. Imagine this, if you have A1, which looks like A11, A12, A13, and so on. A2 is A21, A22, A23, and so on. A3 is A31, A32, A33, and so on. You can just use a diagonal argument that basically proves Q is countable. So you zigzag as follows. Okay. This way you get a single index sequence. So you can call B1 to be A11, B2 to be A21, B3 to be, you just follow the chain, okay? A12, B4 to be A31, B5 to be A22, B6 to be A13, you see, and so on. So this converts a double index sequence into a single index sequence, and the union, and as a result, the union of AI is countable. Right. Union of AI is now just B1, B2, blah, 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 is countable. Okay, so this is a simple proof of that fact. Can you explain the case 1 argument, please? Exactly. So case 1, E is countable. What we wanted to do here, we want to show in part 2, right? In part 2, we want to show S is closed under complement. So we suppose E is in S. Let me just add an extra sentence here to be extra clear. suppose E is in S, right? You need to show X minus E is in scripted S. Okay? Because E can be written as the complement of its own complement. E is countable, therefore X minus of X minus E is countable. This is just rewriting E. Okay, so S is defined this way. If a set is countable or its complement is countable, then it's in S. Here you can treat this statement as the complement of X minus E is countable. So therefore X minus E is in S as needed. Grilling and chilling, is that clear? Okay, I'll repeat. Part 2 is to show S, the scripted S, is closed under complement. So you start by letting E in S. You want to show the complement is in S2. Case 1, E is countable. By a set identity, you can write E as the complement of its own complement. So X minus E quantity is countable. But look at the definition. If X minus E is countable, E is in S, right? So here, that means X minus E is in S, and that's exactly what we needed. So that's case 1 done. Okay, so let's move to point 3. We'll finish that, and I'll call it a day. Okay, well, the stream ends after we finish 3. So, okay, E1 all the way, E1, E2 all the way are in S. Suppose that, and what else? What do we need? We need the union. We need to show the union of EI, no worries, is in scripted S. Thanks for asking the questions, because this is super important. Because here, the definition of sigma algebra is super important. Need to show the union of EI is in S. How do we go about showing that? Well, if all of them are countable, we know from the fact that their union is immediately countable, right? If all of them have, if the complement of all of those sets are countable, then the complement of the union is also countable. So those are the two extreme cases. So what about in between, right? What about in between? So let's say E1 is countable and E2 has countable complement. Why is the union still in S? Huh? This is perhaps a little bit tricky. So let's think about that. So imagine you have a mixed situation. For each EI, either EI itself is countable or the complement of EI is countable. So how do we show that the union is still in S? Let's think of a situation here. So let's think about X as the real. Okay, so let's think about X as the real. If E, let's say E is the rational, of course, E is countable. And the countable is a member of the sigma algebra, and And also you can and also the rationals. The rationals is in S, and the irrationals are also in S because the complement of irrational is rational, which is also countable. So what happens when you take the union? The irrational and the irrational together, taking the union gives you the whole real, and the whole real is in the sigma algebra because even though the whole real isn't countable, its complement, the empty set, is countable. So that does that give us a clue of how to construct the proof in general? So you have a consider a we want to show that the set, the collection of subsets that are countable or have or have countable complements. We want to show that as a sigma algebra. Actually, you know what? Let's do the simple case first. So Vernon says x minus ek is countable. If x minus ek is countable, then the union is a subset. Hang on. Actually, Vernon, I'll get to a point later. Let me just finish let's do case. Okay. So case one, all ei countable. So then by the fact, the union of ei countable. And this tells us the union of ei is in S. Okay. As we mentioned, in our cases, the assumption has to be mutually exclusive. So let's do case two. Case two, the opposite of case one would be at least one ei is uncountable. At least one of ei is uncountable. So how do we go about doing this case? Well, say ei star. Ei star. So ei star is uncountable. Then, because ei star is in S, then x minus ei star is countable. So the thing is, if you have a countable set, right? This is a countable set. If you subtract a countable set by any set, you always get a countable set. Remember, right? The difference, the cardinality of difference cannot be greater than the thing that takes the difference. Okay, so sorry, this is not very clear. Let me just put it this way. So x minus x minus the union of I, x minus the union of ei. Okay, this is contained in x minus ei star. But this is countable. So x minus the union of ei has to be countable. So let's write it this way. So here we're using a theorem called the Schroeder-Bernstein theorem. Now, first of all, this relation should be clear. Yes, that's Vernon. That's what Vernon is saying. If x minus ek is countable, then x minus the unit is a subset. Yes. So since x minus the union is countable, so using a theorem called Schroeder-Bernstein. Oh, case one. Okay. Okay. You said thank you earlier. I thought you understood that. Grilling and chilling. I mean, I'm not criticizing you, okay? So if when I explain that and it's still unclear to you, you don't have to suck it up, okay? And just, oh, I'll just suffer myself. You can just say, okay, this still does not make sense to me. Explain it again, okay? I know you, you think it makes sense now, but if it didn't make sense when I explained it, you can just stop me at that time, okay? Okay, but still, good job for figuring that out. So what I'm saying is here, because x minus union of ei is a subset, exactly as Vernon just mentioned, excellent point, x minus the union is countable. It is a subset of a countable set, so it has to be countable. And we're using a theorem called the Schroeder-Bernstein theorem. Let me just Google that real quick. Schroeder-Bernstein theorem. Once again, this is a basic theorem in set theory. It looks rather obvious, but it's not trivial. Okay, it's not trivial. So basically, it says, oh, actually, hang on. Oh, you don't need the Schroeder-Bernstein, huh? Schroeder-Bernstein is something actually stronger. It says if A cardinality is less than cardinality B, then B, then they have equal. So this is too strong. Actually, you don't need that. You don't need that. So it's just a subset of countable set is countable. Yeah, just a subset. That's all you need, okay? You don't need the Schroeder-Bernstein. Subsets of countable sets is countable. I think for countable sets, we don't need that big theorem. Exactly. You don't need that. You don't need the Schroeder-Bernstein. Yeah. I mismemorized the content of Schroeder-Bernstein. No, you don't need the theorem. Okay. So yeah, if this is countable, then you're done here. The union of EI is in scripted S. So you're done. So we have everything we need. 1, 2, 3. Axioms of sigma algebra successfully verified. So how about that? Okay, so that's it for today. Thank you guys very much for joining the stream. This went better than I expected. This went better than I expected. Well, with some perhaps we skipped a few things, didn't we? I didn't cover the proof of Heine-Borel. We just used it. We didn't cover the proof of Heine-Borel. We just used it. If you guys, you can, I mean, everyone has access to Axler's book, so go ahead, read that yourself, or you can check out my video on compactness, and perhaps, yeah, and do a reproduction of the proof of 2.18. 2.18, even though at 2.18, I have to mention, based on my experience, okay, this is not my first time taking the measure theory, of course, but I try to, for the most part, try not to think too much ahead and put myself in the shoes of a beginner. Okay, I know I jump a little bit ahead and to justify the introduction of sigma algebra, because this is not obvious why a notion of sigma algebra is needed, but basically you want to resolve the internal contradictions between A, B, C, and D. So that's why I jumped a little bit ahead and say, oh, if you restrict mu to sigma algebra, it worked out. Obviously, this is highly non-trivial. It took a generation of work. So right now we're just trying to reap the fruit of that labor. Okay, But at least that will justify the introduction of sigma algebra, and we're going to be studying the properties of sigma algebra quite a bit. Okay, so yeah, we did like one exercise today. We did like one exercise. Do you guys want to see another one perhaps before we go? I feel like it's kind of a bit lame that I only did um, one exercise. So why don't we do a few others? At least let's do two. Let's do two others because my cat stopped yelling. So not yelling, but um, anyway, you know what I'm trying to say. So why don't we do one and two, shall we? Um, the properties of outer measure. So let's give it as a name, sigma algebra. All right, so start a new note. Exercise. This is exercise 2A. Exercise 2A. So let's do exercise 2A. Prove that if A and B are subsets and B outer measure is 0, okay, we want to prove that the union of A and B is the outer measure of A and B is the outer measure of A. So let's do that. Once again, this is an equality, right? Probably you need inequalities from two directions. Okay? How do we go about doing that? First of all, let's try the subadditivity. A union B is uh, the outer measure of A union B is less than or equal to A outer measure plus B outer measure. And B outer measure is 0. So this is just A outer measure. So this is less than or equal to sign. By subadditivity, we have one direction. So there's that. How do we cook up another direction? We want A union B outer measure to be greater or equal to A outer measure. Perhaps a squeeze argument. Outer measure of A union B should be greater or equal to A outer measure. So why don't we consider a bunch of intervals? Suppose I1, I2, and so on is a sequence of open intervals with the union of ik k from 1 to infinity contains A union B. Since it contains A union B, then it contains A. And I think that's pretty much done. Therefore, the union of ik contains A. Contains A. So therefore, the sum of the lengths of ik over k is greater or equal to A outer measure. And taking the infimum on both sides, you get what you needed. Take infimum, the left-hand side becomes the outer measure of A union B. So we're done. Okay, so that's exercise A. Exercise 2. Exercise 1. Okay, next up, exercise 2. Let's go. Suppose A is a subset of R and T is in R, and let's define that the TA is define TA to be T times A. Well, this is pretty natural, right? Scaling transformation. So if you scale a set, and the outer measure of the scale set is T absolute value times the outer measure of A. Okay. So how do we go about doing that? So why don't we consider some special cases first, huh? So suppose, so let's look at cases. Case A outer measure is infinite. A outer measure is infinite. What does that mean? What does A outer measure is infinite mean? Well, that means for any sequence I1, I2, and so on of open intervals, such that the union of IK contains A, for any such sequence that covers A, the sum of, it's case 1, okay? The sum of LIK is infinite. The sum diverges, basically. Okay. So that's the assumption. And now let's consider some situations. So if you have t equals 0, considering the hint, if t is equal 0, okay, let t in real. Okay, let t in real. So if t is 0, then ta by the definition, just t times a, in big A would be just everything is 0. Everything is 0, so therefore TA outer measure is just 0. Right? And it is defined here, right? Here is our definition. It's defined as 0 times infinity. So t equals 0 works out. If t is non-zero, then we're doing a case within a case, huh? Right. So if t is non-zero, then what? Remember, a is infinity. A is infinity. So we wish to show that the right-hand side is obviously infinite, because t absolute value is not positive, times infinity is infinity. We just need to show that. So need to show TA has infinite outer measure. So that's what we need. So how do we do that? Okay, so let's call it J1, J2 of open intervals. be open intervals such that the union of jk's contains t minus a. Contain t minus a. Okay, so let ta be an element in t times big A with a in big A, then cat is very angry. So then A must belong to jk over t, because you can do that because jk times t to the minus 1. A must belong to t minus 1 jk for some k. Equals 1, 2, and so on. So what we're getting about is I want to say A is contained by the union of t minus 1 jk. And here's a quick proof. Here's a quick proof. Let's say I don't like this. Let me just rewrite that. I don't like this. Let A to be in big A. Let A to be in big A, then TA is in T times big A. I don't like that. Let me just modify that. Okay. T is in T big A, therefore TA is in the union of JK over K. So TA is in one of the JKs for some K in 1, 2. I want to show that A is in, so therefore A is T minus 1 times TA is in T minus 1 JK. Okay, so that's what we wanted, which is in the union over K, T minus 1 JK. Okay. Let's put it indeed above. So yeah, this justifies this step. So what's going on now? Well, you have constructed a sequence of open intervals. These are open intervals, so therefore, since t minus 1, j1, t minus 1, j2, blah, 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 is a sequence of open intervals that covers A. It covers A, then we have this by the assumption. The sum over K, the length of t minus 1 jk is infinite. Right? So therefore, what we have? Well, we have the sum of over k, t minus 1 absolute value, length of jk is infinite. Well, what does that mean? Well, this means the sum over k, the length of jk is infinite. So what we have, let J1, J2, P2 to be open intervals such that it covers TA. Then we have, you see, the length of JK is infinite. So therefore, this is what we're getting at. So therefore, the TA has infinite outer measure in this case. So as needed. As needed. So that completes case 1. Let's do case 2. Let's do case 2. So here you have a finite outer measure. Okay. The outer measure is finite. So what do we do? The outer measure is finite. Let A have our finite outer measure. Let's say if we have one direction, can we prove the other direction? If we already have TA to be less than or equal to T absolute value times A. Actually, you know what? Let's consider trivial case first. If T is 0, okay, if T is 0, so that should be easy. If T is 0, once again, TA is just it's just a 0 set, just 0 again, which equals 0 times A outer measure, which is T absolute value times A outer measure. So that's the trivial case taken care of. So let's assume T is non-zero. So let's assume T is non-zero. So in the case of T is non-zero, if we have one direction, do we immediately have the other direction? Do we immediately have the other direction? I'm not quite sure, huh? The other direction is TA outer measure greater or equal to T absolute value times A. So can we write A as T reciprocal TA, huh? Can we do that? I think we can. If you multiply T and divide by T, you get the same set. And then you apply the first result. So this is T reciprocal TA less than or equal to. So multiply T absolute value on both sides. And that's exactly what you wanted. So you just need to prove one direction. You immediately get the other. Right, so this is inspired by the proof of translational invariance, which we prove one direction and you immediately have the other direction. So that was my original motivation, learned from this trick here, right here. Okay, so let's just prove one direction. So can we prove one direction? How do we prove this? Well, let's prove one direction. Let's basically prove, start with TA outer measure. Okay, so let's start with, let I1, I2, blah, 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 be a sequence of open intervals such that the union of IK contains TA. Okay. the TA. Okay, so well, using the same argument as earlier, and using an argument earlier, you can immediately get a union of K T reciprocal IK contains A. Contains A. So we have the sum of the lengths of T reciprocal IK over K is greater or equal to the outer measure of A. Right, just use this. And the length of the scaled interval can be easily expressed as T reciprocal absolute value, the length of IK, greater or equal to A outer measure, multiply T absolute value on both sides, and you get the sum over K, the length of IK, is greater or equal to T absolute value A outer measure. But we know taking the infimum gives you the outer measure of T. Oh, actually, we proved what direction? I think we proved one direction, no? Yeah, we proved this direction. We proved this taking the infimum. Taking infimum over, by the way, taking infimum over all I1, I2, you get the outer measure, because here I1, I2 covers TA, right? So taking infimum on the left hand side gives you the outer measure of TA give you the outer measure of TA. Okay. So to get the other direction, note A equals T reciprocal TA. So therefore apply that A outer measure equals T reciprocal TA, which greater or equal to T reciprocal times TA outer measure, and then you multiply T absolute value, it gives you T absolute value A greater or equal to TA outer measure. So combine 1 and 2 gives you the result. TA outer measure therefore equals T absolute value A outer measure as needed. So overall you have the full result. Okay, you take care of all the possibilities. A outer measure is infinite, A outer measure is finite, t equals 0, t non-zero, everything is taken care of, then you're done. Okay, how about that? I think it's a good time for us to call it a day, and I encourage every one of you to try out the exercise yourself. And if you have questions, send it to the Discord server. If you haven't joined the Discord server already, this is exactly what it's for, and for other things, obviously. So yeah, I hope we can have tons of exercise discussion in Discord. That would be amazing. Okay, but basically, I think it's a good time for us to call it a day for our run. This is what's typical on the channel. 4 hours is infimum, actually. If there's no technical difficulty, 4 hours is infimum. Typically, we go for at least 4 hours and sometimes 5 hours. But I think right now it's a good time to stop because I'm getting a little bit tired and I'm losing my voice. All right, thank you guys very much for joining the stream, and I'll see you guys next time. Next time would be Saturday morning, mathematical finance, and the next one would be Saturday evening on mathematical statistics. Bye, everyone.